Welcome everyone. So this is day one of the Building Energy Modeling Fundamentals and Applications. Myself and Drew will be splitting it up for the presentation for the next 2 days. So thank you for being here. We'll run through some housekeeping items to start. Get it. Again, copyright. Development. So this is again partially developed through BEPSA USA, which Drew and I are both part of. This course is registered for AIA, so you will get hours for it. You'll also get GBCI hours if you need them as well for your lead accreditation renewal. So who are we? My name's Sam Mason. I'm the director of Code Green. And yeah, I'm a professional engineer, building energy modeling professional. Been doing this for about 17 years. And Drew, I don't know if Drew, you want to give a quick intro?
Sure. I work for Bentley Systems, and my focus is energy performance and urban modeling, digital twins, sustainability. But I've been doing energy modeling since university days.
You're not going to say how long that is, are you?
No, I'm not.
But the prerequisite is you have to have a beard and it has to be going white. That's kind of the, that's what we say. So anyway, thank you all for joining. If we were a little bit smaller group, we would kind of ask around and spend some time understanding who's there. We have a class list so we know who the attendees are. We're a big enough group today that we can't really do that because it would eat into more of our time. So without further ado, we're just going to jump right into it. Today is roughly going to run a little over 3 hours, so hopefully people can hang on at the end for a little bit to cover the whole day today. So again, we're going to run for a little over 3 hours today, and we'll do the same for tomorrow. So what is the general objectives for this course? There's 5 sort of main things, and we'll kind of hit back on all of these as we run through the fundamental pieces and some case studies. Some other standards and things that you should be looking at when you're doing building energy modeling. So, the big one is identify appropriate questions and that you're going to evaluate and how to use a model to do that. So we'll talk about a bunch of examples of framing the analysis correctly, using the appropriate tool, getting good input sources, getting good data to use in your model. Your model is only as good as the data that you're putting into it, right? Next one is look at QA/QC processes. So, making sure you're tracking inputs into your model, you're doing review on the results, and keeping track of those in an organized manner. And we'll talk about some ways to do that. Next one is how to, work within a design team as a building energy modeling professional or as a, someone who is running a model. Like, how do you actually communicate the data? What does your timeline look like? Generally, timing is the biggest constraint that modeling has. The data needs to be produced very quickly. So, we'll run through a lot of examples of how to present that data, what level of analysis would be required at certain phases in the design process. And last is develop an overall project plan. So again, this is looking at more of the planning side and understanding each phase, how much time it might actually take, the fees associated with it, level of effort required. So, and there's lots of monikers out there of what people call energy modeling software. The one that we will reference and continue to use is BEM, which is building energy modeling. So that covers sort of everything associated with energy modeling, energy analysis, that sort of stuff. But we'll use BEM as the moniker for today. So again, quick intro, this is kind of geared towards anybody that is either doing building energy modeling themselves or considering doing it, or someone who is interpreting results for building energy modeling. So, if you're receiving a report and you want to be able to understand if, what does it actually mean, this is also a helpful class for that. So we're going to look at a lot of case studies, exercises. We are not going to go in specifics of a tool. We're not going to talk about how to use Energy Plus or eQuest or Bentley or IES or anything like that. We will show you what goes on under the hood behind a lot of those programs, but we're not going to talk about a specific workflow through a specific tool. The intent is to be able to use what we present today in any tool You just have to know that tool, right? So we're not intending to tell you which tool is better than others. The areas of emphasis we'll talk about is again, really making sure that you have a clear definition of what you're trying to achieve with doing the model, making sure that the quality is maintained, accuracy is maintained, and that the work we're doing actually has an impact, right? It actually makes an effect on the design. It provides good data for someone to make decisions on. And other things to know is that, you know, if there's tons of data and you can really get super detailed in certain things, but no one person knows everything, it's always good to have some backup and somebody to review. So, but it's a constant learning process. And so that's, you know, a good reason why everybody's here today is to learn, you know, learn more about the process. So today we're going to run through the overview. We'll do, which is a fairly extensive section of like, what is energy modeling? So it's kind of a high level, and then getting down into a little more specific. We'll look at one early design project of how you would use modeling. We'll talk about ASHRAE 209, accuracy, uncertainty, and we're also going to move that weather section into the first part today. And then tomorrow is a bunch of examples. So we're going to run through lots of case studies, examples of how you model specific systems and tools, or specific systems, not tools, specific systems, specific sort of ECMs, things you might be looking at for analysis, and some existing building examples. So, all right, with that, we'll get into it. So the first section here is the overview. So we're going to cover a lot of stuff, but really the big one is, you know, what happens when you run a simulation, and what sort of information do you need, right? And then on the back end, what sort of information comes out of the model. And we'll run through all this. I'm not going to read everything, but the big question is what is the engine doing in the background? You know, what does the data come out? How can you use it? And who is doing, you know, generally who is doing energy modeling? So when you run a simulation, what are you doing? You're identifying a building design. So again, you might have a building, you might have a theoretical design, you might have an existing building, who knows? And we'll run through lots of options for those today. But you have a set of building characteristics, so inputs that define that building. And so, you know, walls, roof, lighting, HVAC, that defines the building energy model, again, a 3D representation of the model. You apply an annual hourly weather data set on top of that, and you run the simulation. So that, you know, is the highest level. And then on the back end, you get a bunch of data on you know, what the building actually did. How did it respond to that weather data? So it'll tell you how much energy is being used, what are the loads in the building, all sorts of stuff. And we'll look at all the different data that comes out of that. So why would you do energy modeling? And this is a really good first question to ask is, you know, and a lot of times, you know, maybe there was an RFP that came out that said, you know, we need to do energy modeling for code compliance. I'd say that's probably, you know, one of the most common. The second most common would be for some sort of green building certification, like a LEED certification, right? So generally those are a common reason that they could be there, but there's a lot of other reasons to do it, you know, both for research, you know, energy code is driven a lot by energy modeling, so the policy development. And the big one that we like to focus on is optimizing performance, right? So, you know, you have a design, but how can you make it better, and how can you do that cost effectively? But there's lots of other things to look at, right? You can explore different ideas, different alternatives, you know, challenge different rules of thumb. You know, a lot of times a design engineer will be giving you a, you know, a CFM per square foot or a ton per square foot value, and that's how they've sized their equipment. But you might run the model and find out that, you know, the envelope is much better performing, and you only need, you know, half the capacity that they've sized, right? So it's a good feedback mechanism as well.
Sam,
yes,
just a second. Some people are reporting audio garbling. Maybe it might be time to lose your
okay,
your cam.
I will try it and see. Hopefully we'll see if this is better. I will also move closer. I guess let me know if there's any other comments about audio. All right, continuing. So other, you know, reasons to do modeling would be, you know, tracking performance. Again, this is sort of looking at like if you had a new design project, you designed it, you modeled it, how well did it actually perform against what the model said once you get real utility data. So so one example of that could be, what happens when you increase window area in a building, right? You could have very, low window to wall ratio, sort of a code requirement window to wall ratio, and then you could have, almost a fully glazed building, right? So that would be a great answer, a great thing to use modeling for, to answer, how much energy use or the size of the peak sort of cooling and heating loads that would be associated with each of these options, right? So. Another thing you could be looking at would be, sorry, now I'm getting computer problems. Okay. Another thing to look at is look at how the envelope is, contributing to peak cooling load, right? So you could look at the components of your individual, envelope, like the walls, the roof, the glass, and see which one has the largest impact on peak cooling, right? So that could give you an idea that in this case, maybe you want to look at, reducing the solar heat gain to minimize cooling load in your building. You could also be looking at EUI, right? So which end use in your building is contributing to your highest EUI for your building, so your energy use intensity. So that might, again, give you an insight of places to look to try to reduce energy consumption. So the other thing you could say is, what does your massing impact have on energy consumption, on cost, carbon emissions? So carbon emissions are becoming a more common way of reporting the results out of a, annual energy performance out of a model as well. So other things that you could be answering, is it going to meet 2030 challenge, right? Can it be net zero carbon? And then once you maybe have the answer that it won't meet that design, what sort of changes would be required to get it to meet the net zero requirements of the 2030 challenge. And a way of, looking at, just representation of how you could show this data, you could be looking at 4 different alternatives. This could be envelope or HVAC, whatever it is, but you could have a target where you have an EUI that needs to be, say, at 22. You have a bunch of design alternatives. A good way to use modeling is to graphically show the results of which one of the options will actually get you to your target. So other things, you could look at feasibility for, natural vent and free cooling, or certification, right? It could be that you're doing feasibility just to see if you can meet minimum requirements, or you could get to LEED Platinum. Look at savings from potential control options on lighting, and all these sort of impacts of things that might actually happen as a result of design changes. And you can test those all out with the model, right? So it could be cost, emissions, sizing of equipment, whether you're meeting energy code or not. So, and normally we would stop and ask. I mean, I guess we could just say raise a quick poll to people that are online, or in the chat if you want to respond, of how many people have actually completed a energy model, whether it be a block model or full building model, compliance model, whatever it is. We just like to understand a little bit about what people are doing professionally if they're using modeling. So feel free to respond in the chat. Cool. Okay. And I can't see the chat, Drew. I don't know if you.
Yeah, I can. Sean says only reviewed. Jose said yes, he's used it. Matthew says yes. Kara says haven't performed energy modeling before. Luke says have reviewed model but started one from scratch. Done a few, yes. Jorge says my group is reviewing Open Studio. Luke has not. Isaac has not used it. Mohammed, yes. Keith has done one in TSPR, one in eQuest. Zay says, is cooling heating loads calc energy modeling? And I would say yes to that.
In some senses, yes.
Well, it is. It's modeling. It
is modeling. It's
maybe not full annual modeling, but
yeah.
Craig says yes, he performs and reviews. Jing Wing says I did energy modeling. Jacob hasn't done any yet. Jose's done many. Asia, yes. Andrew has reviewed but not performed. Asia done several. Margaret, yes. So we've got pretty good response here.
Okay, yeah, so it's kind of some people yes, some people a little bit, some people no. Okay. Yeah, I mean, I think the intention is that regardless, you'll kind of see at least a little bit different, you know, potential perspectives on how to use modeling and how to present the results for modeling as a result of this. So thank you everyone for responding. That's very helpful. And the question of heating and cooling loads being energy modeling, it is certainly a component of doing a full building energy model. I'd say it depends. I guess sometimes people are using heating and cooling load calcs just to do equipment sizing. That is a little bit different approach, although a lot of softwares and a lot of companies are now combining and kind of doing their load calcs and their energy modeling at the same time. So it really does depend on what your aim is, right? Where an energy model is kind of looking at annual whole building performance, whereas your cooling load is likely only looking at sort of your 3 to 4 month peaks to get equipment sizing. So all right, we will continue to move on. So what sort of information goes into an energy model? And there's a lot, right? And the data that you will be inputting into the model, and how detailed you get will depend on the stage sort of you're at in the design process. It also will be dependent on, what the goal is of what you're trying to achieve with the model. So if you need more accurate results and you need more, detail, to try to help make sort of bigger capital decisions, you probably are putting more time and more effort into the inputs. If it's early phase, you're probably putting less time into it. And we'll look at a couple examples of both of those. So what generally is included? You're putting in geometry, obviously, in your envelope. So you need to enclose your spaces. You'll put in any sort of heat gains that you have and schedules associated with those gains. Any infiltration or opening, windows and doors that you have. You will have HVAC. So again, we'll spend a lot of time talking about HVAC, but in general, you're putting in a full description of your HVAC. You could also include a lot of other systems. Again, these may or may not be pertinent to your building. They may or may not have an impact on what you're trying to analyze, but certainly for certain, code or lead requirements, you would need to include service hot water, exterior lighting, vertical transport, kitchen equipment if you have it, and renewable energy now, which is part of the 90.1 standard starting in 2022. So, and then you also put in utility rates and where your energy is coming from. So, and again, this can be done in the tool. It can be also post-processed outside of the tool, but most tools are capable of taking complex rates. So, and the format and how you actually input this will certainly vary widely depending on the tool. And again, we're not going to run into how to do this in a specific tool, but again, this is giving you an overview of what data would be required when you need to go collect this data. What are you looking for? So what's included in the geometry? You're looking at surfaces. So you're looking at, what kind of exterior surface do you have? This will obviously impact solar and gains and mass essentially of your geometries, interior surfaces, and then fenestration details. So you could be looking at a building, which is just a collection of spaces, built up. Again, this is kind of how you're starting to build a model, is that you're modeling a bunch of spaces and they're combined into a building. You could have shading. You will also be defining the thermal properties for all of your opaque surfaces and your fenestration components as well. So you'll be putting in the heat transfer sort of performance of all of these different components. On the opaque side, generally you might get some sort of built up assembly. So you'll have a stud assembly in this case that has insulation between cavity members, in between where the framing is, with gypboard and a plyboard. And again, what a software tool will do is they will either automatically calculate this hypothetical combined performance of your insulation and framing layer, or you will need to do that manually outside and input that into the tool. So But the constructions generally are just a set of material layers, and each one of those materials has a conductivity, specific heat, and density associated with it. So again, a lot of tools will have a database that has certain properties, or if you want to create your own, you can do that. You can create your own custom sort of makeups. But you also need to be aware that the solar absorptance and how much actual radiation is being emitted from materials is also fairly critical, particularly if you have high mass surfaces, or high solar gain areas.
Sam, we have a couple questions here. Is there a common type or way of sharing building envelope data? And same question for HVAC equipment.
Of sharing and
building envelope data or HVAC equipment data?
Sure. I guess it depends. And it's from Jose. I guess for a new construction project, you're probably looking at through the drawings, and you're looking at the specifications to figure out what it is. I don't think there's a common methodology in terms of like a format that you end up. I mean, I'll show you a few examples of what it looks like, but yeah, I mean, you're usually looking at total system performance when you're looking at wall assemblies and then glazing assemblies and things like that. In existing buildings, it might be site surveys of where you're sharing it across different software platforms.
Yeah, Jose clarifies it's for sharing across different software.
Right, not necessarily. Generally, you're going to be recreating it. So as an example, going from a BIM model into a building energy model, a lot of times the assemblies that are generated in the BIM model, the building information model, don't necessarily translate to a true thermal performance of an envelope system. So for the most part, you're going to be recreating those in whatever tool you're using. Yeah, sorry, there's not a great answer. We can certainly follow up with their specific software to software that you're talking about, but for the most part, no, you're going to be recreating that. You'll be translating drawing information into model information. So just a few examples again of data that you might be pulling in, insulation versus steel and wood property. But again, this is all what's needed and required. Again, the specific heat density and conductivity all will have a fairly large impact on how fast heat is being transferred through into the space. So how fast a conductive load shows up as a conductive heat gain actually shows up as a load in the model. So good thing to be aware of, and we'll hit on it a few times today about mass of assemblies and how that actually will impact energy performance. So again, just going back to the same sort of situation where you have cavity insulation. In this case, this is a metal framing, so a metal stud wall. If you were to put in the full cavity, R value, in this case, you'd be overestimating sort of the performance of the wall, right? So what you need to do is put in an effective R value for that layer. Again, some tools will do this directly. The place that I like to use, and I recommend at least as a starting point, is to look at Appendix A of Standard 90.1 2019, which this is for metal. They have this for wood. They have it for mass walls as well, where you actually have tested values of certain spacing and stud sizes, how much insulation, and it gives you an effective R value. So for a 2x4 16-inch, if you're putting R15 in that cavity with a metal stud, you're only getting 6.4 effective out of that layer. So again, that's a much different performance than putting R15. So that could certainly change the results of your model quite drastically. So that's a good place to look, just to make sure you're using realistic values for combined stud and insulation layer. On fenestration side, you're usually getting a U factor, and in many cases you might be getting like a center of glass rated number, which is not all that helpful because it doesn't account for framing. But if you're getting an NFRC rated window, for example, a whole assembly, that will give you frame plus the glass performance, and that's really what we're trying to achieve, is to get the whole system U factor. And again, many simulation programs will allow you to put in a center of glass and a frame, and it will do this sort of calculation for you. you know, the more accurate you can be about that, those inputs obviously will give you better results in terms of your loads that are resulting from your fenestration systems. What also is included with fenestration is solar heat gain coefficient or shading coefficient and visible light transmittance. In some cases, you will also have air leakage rating as well, which you can use for inputs for infiltration. So, and you can get much more detailed than this instead of just using a single number. Obviously, there are spectral variations when the sun moves through, you know, the course of a day. You know, solar radiation hitting a glass at an angle certainly has a very different amount of radiation that passes through than if it was perpendicular. So you can get much more detailed. You can get into some other simulation options and some other software tools that will import more full spectral models for glass, and we'll talk about that later today as well. In terms of heat gains, what all is included? You have lighting, you have equipment, you have people. People obviously give off heat. And then you have schedules associated with those. So you need to have a schedule that says, you know, when are the lights on, when are the lights off, and how much light, you know, how many of the lights are going to be left on at night, whether it's emergency or otherwise. So you need a wattage input, you need a schedule. For lighting, you also need to understand how much radiant gain versus convective gain is associated with your fixtures. So again, this can be you know, fairly important, especially when we start looking at LED lights where you might have drivers that are, you know, up basically in the ceiling. You might have, you know, a fairly low sort of radiant gain into the space from your lights because most of it might be actually, you know, headed directly basically back into your return air duct. So, you know, good to know if it's a recessed fixture, that's likely the case. If it's a, you know, a surface mounted or a hung fixture, you know, you might have a lot more of that heat actually ending up in the space. So it's good to understand how much is actually a load in the space versus how much is heating your return air or a plenum space. Equipment, the same thing. You'll have an input for power. We'll talk about estimates of where that number would come from and a schedule. And the same thing, you'll need a radiant split and a convective split. And then people, same thing. You have number of people. In general, there are you know, tables that will give you an idea of how much heat, both sensible and latent, that an occupant will give off, depending on the activity that they're doing. So, you know, if it's a gym type of space or, you know, workout space or something, people are going to give off a lot more heat and a lot more sensible and latent heat than they would if it was just in the typical office space. So, good thing to understand. People give off moisture that needs to be dealt with by your HVAC system. In terms of infiltration and or natural ventilation, again, there's a couple ways typically that software tools deal with this. More focused on infiltration is because that's sort of a standard. Natural ventilation is a little more unique in that it's not modeled for a lot of buildings, not applicable in a lot of buildings, but generally you're looking at opening area, which can, you know, either be a crack length or a width or potentially like an air change per hour, you know, an air tightness number. Location of that, those openings, whether it's windows, doors, otherwise, so you might have a higher rate lower in the buildings and a lower rate higher in the buildings, so you could have stack effect issues as well. But you also have a schedule. And generally, this is the schedule that's shown here is pretty typical for a building that has a central HVAC system where, you know, when the HVAC system comes on, you're kind of slightly pressurizing the building a little bit. So your infiltration, you know, as a percentage of total infiltration is maybe going down to 25% when your HVAC system's on. So you have a much lower percentage infiltration load. But at night when your system turns off, you know, the building is getting a lot more infiltration as there's less, you know, positive pressure from the fans that are in the building. So again, but you need a rate and you need a schedule. So those are things you would need to collect or make estimates for. On the HVAC side, again, this is the most complicated piece of doing, you know, building energy modeling is describing the HVAC systems generally. But you'll need to have a pretty good understanding of the zoning. So where are your thermostats located? How is your heating and cooling distributed? You'll need to understand ventilation rates, so how much fresh air is being introduced. The types of systems, which we'll spend a lot of time looking at all the different permutations of HVAC systems that can be modeled. how heating and cooling is distributed, whether it's air, hydronic, how you're generating cooling, so how you're cooling the space, how you're heating the space, how you're controlling humidity, and then schedules and controls. So we'll step through each one of these now. So thermal zoning. So your zones in a model might not necessarily be the same as actual HVAC zones, because you might have, a lot of similar adjacent spaces that have same functionality. In an energy model, in that case, it's appropriate to combine, similar zones as long as they have similar characteristics. But, thermal zone could be a single room, it could be a set of rooms, it could potentially even be part of a room. So if you were to look at how you would zone out this space, you could have single room. So you have corner rooms that have exposures 2 directions. You would probably want to put those on their own thermostat because they're going to see different loads throughout the day. The red zone here might be, conference room, so it has a different use schedule than the rest of the spaces there. And the purple one might be a, storage closet or IT space or something. Your thermal zone could also be a set of rooms. So in this case, let's assume these are all exterior private offices on a typical office floor. Those 4 rooms are all private offices. They have similar occupancy. In your model, you might group those all together instead of making 4 individual zones. So that would save you some time in terms of actually creating the zones, and in terms of simulation, it would speed the simulation up. And finally, you might have a portion of a room. So if you have a large open office space, for example, here, you would want to zone your facade orientations separately so that your glass, that's facing, in this case, to the east and to the south, you want to put those on separate zones within your model, because you likely will have separate thermostats serving those spaces. And then your core zone would be, modeled separately as well. And so it might not exactly line up with your thermostats, but again, you might want to overlay thermostatic zoning on top of this as well, just to confirm. And we'll show a couple other examples of this later today. So ventilation rate, generally there's 2 things you need at a minimum to understand how ventilation is being, introduced into the building. You need to know the rate, so, CFM or liter per second that's being introduced, and how that is being controlled. And there's lots of control options. It could be a scheduled time of day, it could be DCV, it could be, time clock. You might have economizers as well that need to be accounted for, but at a minimum, you need to know what that minimum rate is, and how it's being controlled. In terms of HVAC, there's, again, lots of permutations, but we've got 3 sort of main systems that you end up having different permutations of as you build out larger, more complex buildings. You can have single zone systems, so it's fully contained within a single zone. You could have multi-zone where you have 2 adjacent thermal zones being served by the same system, and you could also have just local zonal systems. So this might be more like a fan coil or a research system that doesn't necessarily connect to a larger central system. But most of what we're going to model, most of what you end up modeling is some sort of permutation of this, right? You might have, instead of overhead zonal systems, that might be a perimeter baseboard, right? That is controlled separately from, say, a central sort of heating or cooling system, where you might have VRF coils, you might have distributed heat pumps. It's all sort of comes down to these sort of 3 setups. And then there are some other slight variations of that, again, which are again a little bit different than what we said, but you could have some radiant heating and cooling. So that could be slab, it could be baseboards, chill beam, something like that. You could have dedicated fresh air as well. So most simulation programs these days are capable of modeling a lot of these, options and different permutations and combinations of systems as well. And good old natural ventilation, which some tools are better at than others. We're not going to spend a ton of time talking about it, but there are algorithms in most of the models that will account for, natural ventilation and how windows will be opened and closed based on schedules or, occupancy, things like that. Question there is, what is zonal? That's more just like a research fan coil or a fan powered box or something like that that doesn't have any connection to the main system. So it might just be, a fan powered box or fan coil. It's sort of more typical for a zone level control or zone level HVAC system. So what else do you need in terms of describing the HVAC? You'll need to understand how, heating and cooling is distributed. So in this case, you'll be looking at fan, at airflow, power, and how fans are being controlled to distribute air in case of an airside distribution system. You need to understand, the pump. In this case, you have a hydronic coil or a refrigerant coil. In either case, you need to understand the flow of the pump, the power, and how that pump's being controlled.
Going
back to the zonal VAV. Yeah, so a VAV could also be considered a zonal system as well. So that's what I'm saying. The permutations, once you kind of overlay typical systems, yeah, it could be a VAV, it could be a fan-powered box, something like that. Something that has a coil and a fan in it. You also need to define how cooling is being provided. So you've got, options, pretty typical ones here. You've got packaged sort of controlled systems. We're seeing more commonly multi-split, DX type systems. We have refrigerant coils. Water source heat pumps might be an option with a cooling tower, ground heat exchanger. Again, these are all sort of DX based direct expansion type systems. You could also have chilled water, so you might have a chiller that's providing that. Could be air cooled, water cooled with the tower, or you could have hybrids of this, right? We're seeing a lot of this, where we're getting combinations of geothermal with other system types where the geothermal doesn't have enough capacity to provide all of the heating and cooling for the building. And what sort of information do you need to define how the cooling is being created for the building or generated for the building? You need to understand the efficiency of the equipment, so the DX coils or the chiller. You understand the capacity of those pieces of equipment and how those vary under different conditions. So equipment does not operate the same based on all return temperatures or outside temperatures. So example for a packaged DX air conditioner, rooftop air conditioner, has a rated outdoor air temperature at 95, and in this case an EER of 10. But the software tool, the building energy modeling tool, again, most of them will have this built in, but depending on level of complexity, you might want to build the actual curve. If it's hotter than that, it will have a lower efficiency. If it's cooler than that, it generally will have a higher efficiency for cooling systems. So you need to be aware of how the piece of equipment operates over the course of all potential outdoor air conditions. It also will, cooling capacity will also change as a function of outdoor air temperature. So you get more capacity as it gets cooler, less capacity as it gets hotter. And efficiency will also vary based on the load on the system. So, you might be looking at your system operating at sort of an 80% part load throughout the year and understand that, in this case, for a small DX that doesn't have a VFD on it, it's going to be a little bit less efficient than at full load. Again, all characteristics that usually are available to input for most modeling tools, but you need to gather all this data as you're collecting your inputs for your model. And on the heating side, very similar. There's a lot of different types out there, but you need to know the type, capacity, efficiency, and again, the performance under varying conditions. So you might have single zone sort of electric, or gas kind of unit heater type systems. You could have hydronic hot water with boilers, heat pumps. You could have air source heat pumps on rooftops, multi-splits as well, water source heat pumps with the boiler, ground loop heat exchangers. So again, very similar, and you could have combinations of all these kinds of systems as well. So in terms of schedules and controls, there's, you can go very basic within a model. You can also get much more complicated. These are sort of very simplistic, minimal control requirements that need to at least tell the system how to run, right? So when are your fans on and off? What are your set point temperatures? So in this case, you have, 74 degree during occupied hours, and you have a setback to 85. And on the heating side, set back to 60, and a design temperature indoor on your thermostat is 70. So again, at a very minimum, you kind of need to know the hours and set points. You could also have humidity controls depending on the space type at a minimum to maintain, stability of your systems. But again, it can get much more complicated, and we'll talk about a lot of other options in terms of resets and other inputs you could use for controls of the HVAC system. So you can have controls both on air side and water side, and both on temperature, again, also humidity. It also really just depends on the type of system you have, whether you have hydronic-based or air-based systems. But you could have, again, like I said, constant. We have a fixed set point that's not modulating at all. You could have lots of different options for resets. So this is just an example of a supplier temperature reset controller, right, based on outside air. So very common, required by ASHRAE 90.1. But again, you could have various permutations of that that could be implemented within the model. And then actually controlling your fans or pumps, again, that could be variable flow, constant flow. And again, there will be a curve that defines how that pump or that fan operates over all the various flow or static pressure requirements. So again, we'll run into these more. This is kind of just the intros. And then what other systems? Again, we talked that this might be included. You might need to model it, you might not. If you're doing code or lead, you need to include everything that consumes energy. So you would be including all this, but you might not include it. So service, hot water, lighting, other sort of process loads, elevators, kitchens, renewables, energy storage. So again, just an idea of what you might need to be gathering. And then on the utility side, again, depending on the level of sort of accuracy of you're trying to get in terms of expected utility cost, you might need to get into the full weeds on the rates. You might just be using very simplistic, EIA average state rates for your energy cost, right? So we also need to gather source energy factors. So these are becoming more readily available based on the eGrid location. So, how much actual primary fuel is being burned, or whether it's not primary fuel being burned, or, generated from renewable sources, how much of that is actually making it to the site. So there's losses from transmission and generation. A pretty good reference is, at least for now, on average in the US is about 2.8 units of primary fuel results in 1 unit of site fuel. But it does vary quite widely. You'll see, I think for New York right now, that number's at 2.4. Certain places, it's over 3.5. So, but if you look at the eGrid, it gives you a pretty good idea of those rates by location of where you are in the US. And a question about variable versus constant CO2 energy factor. Yeah, and certainly there, this is kind of just, if we were to consider everything constant, right? There is a move towards looking at the hourly or sub-hourly, generation, and whether it's coming from renewable sources or non-renewable sources, and what that actually means in terms of like CO2. So some municipalities are reporting CO2 just annually as one number. New York State, for example, is going to start giving that data hourly from the previous year, so you can look at actually how the grid, varied hour to hour over the course of a day, or seasonally how it was actually, how much CO2 was being generated per kilowatt hour generated. So to that point, this is the breakdown of CO2 emission factors. This is current for 2020, so there is updated 2023 data, but it's not fully complete at this point. Giving an idea though of how much carbon emissions are being generated by basically location on the eGrid. So, so these are the individual eGrid subregions. So this is how the electric grid is being broken down in the US in terms of distribution and fuel generation. So it's a little bit different than if you look at how the grid is actually organized. There's sort of 3 main grids in the US, but this is getting to the subregion where the Department of Energy is actually watching generation sources, and they're looking at where electricity is being generated, how it's being generated. So average is about 820 pounds per megawatt hour, and you'll see that varies quite widely when you look at Hawaii, which is basically burning fuel oil for the most part, all the way down to New York, which is sort of at the 233, which is mostly hydro and yeah, hydro from New York and from Quebec. So
yeah, a couple questions here. Somebody asked about block rate. Explain that.
Yep, we'll go back to the block rate. Okay. I don't think I have a graphic for it, but yeah, block charges could be that you are, you're basically charged for every incremental block of energy you're using. So, it could be the first 500 therms, you're paying 20 cents a therm, or you're paying some, bundled rate for that first 500, and then you get to the next 500 and the price might change. You might be paying 25 cents. So it's again, just the volumes of energy, whether it be, a gas source, a fuel source, or an electric source, are charged at a fixed block rate. So you're getting a certain number of units at a certain fixed price, and then the next block has a different price associated with it. So not all that common anymore. It's more common for smaller. I see it a lot more commonly in like smaller multifamilies, where it's those block charges these days.
Yeah, a couple other questions. Variable versus constant CO2 energy factors.
Yep. Yeah, that's what I was saying. There are, the numbers that are published from eGrid are which is this slide here is the eGrid data from 2020. Again, these are fixed values that are calculated from the average of that total year, right? So they looked at all generation sources and divided it up by total amount of electricity generated to come up with the output emission rates. So this is, again, using a fixed approach. There are, again, pushes towards having a actual hourly factors available depending on day versus night generation and seasonal generation. And then the acronyms here, these are the individual eGrid subregions. So I don't know the name for all of them, I'm not going to remember, but this is, again, just acronyms of how they have named out the individual regions. So you can go, if you look at eGrid, you'll see it'll explain exactly what the name of each one of those is. I don't remember what they are. So, and then is there eGrid side? This is the eGrid side. Again, it's not labeled as such, but again, going from source to carbon emissions is where we're kind of stepping towards. And so again, this is for electric. On average, is at 818. Natural gas is down at 117. So it's substantially lower. Again, you're basically just transporting gas at that point, so it's not. And there could be the same, accounting that needs to be required. So if you have a district chilled water system, you might have, CO2 emissions that you need to gather for that specific plant. If you're on a central campus or, on the DC system, for example, or something, or a district steam system like they have in New York City. So those will have a rate for them as well. But again, it's a good way to compare. Again, that might be a metric that the client is interested in reducing their CO2. A lot of the building performance standards that are coming out and being enforced are related to CO2 emissions. So a lot of times you'll use your model, you'll calculate how much electricity, and then you will need to translate that to CO2. And that's a good point back to this constant versus variable CO2 factors, and that you might get very different results if you use a fixed, emissions rate for your building for the year versus using, the hourly emission factors. And so when you start looking at the varying rates, again, this is looking at long-term CO2 pattern. This is total for the US. When it's more less carbon intensive on the grid versus when it's more carbon intensive, you'll see that, in the summer, sort of middle of the day is kind of the least carbon intensive. And the reason being there is that we have a lot of solar on the grid, right? And so that's when you kind of see the lowest, at least current right now. And then at night and in the winter is when you have sort of the highest emissions on the grid. And that's generally because you have less renewables, you're burning more fossil fuels. And there's a lot of data here. The NREL Cambium site is really good for this. It's a little hard to get started in, but once you get in there, you're able to pull out these hourly data files, fairly easily, and you can kind of do some planning and do some constant versus time varying CO2 calculations. So again, depending on what you're trying to get into, it could could very much be a deep dive on CO2 emission factors. So we'll do a couple simple examples here of what the boundary might look like for an energy model. So if you're early on and you might be doing, a simple box model, you might be modeling a single room, looking at glass basically on two different directions, looking at loads, looking at, sort of HVAC system selection maybe. You might be modeling a whole building. You might be modeling, a parking lot associated with it. Depending on where you are, that parking lot might be a big chunk of your energy use. It has a lot of lighting, lots of electrical vehicle chargers, whatever it may be. You could be looking at renewables as well. You could also be looking at multiple buildings on a site. So this could be a campus. So the permutations, of where you draw the boundary of what you're actually modeling also needs to be something you consider up front. So in a big city, again, you might also want to be including the adjacent building, right? Because that might reduce output from potential renewables. It could also be shading a significant portion of your building, and reducing solar load throughout the year. So again, something to consider in terms of where you draw the boundary. So quick quiz. I'd like everybody, if you can, quickly respond. Which one of these inputs to your model, so energy model input, will have the biggest impact on results? And we say results from both a, say, energy cost or carbon point of view. I'll give people a few seconds to. Okay, so I think, yeah, Richard Thompson, I think, got the main point is that this is it's a trick question for all purposes. It really depends. It depends on the project. It depends on the climate zone. It depends on the motivation of doing the model. If it is a reduction of energy or carbon or cost, it could be any number of these things. It could be multiple inputs. So yeah, the size of the building could also certainly make a big drastic of window area versus something else. So the idea though is to understand before you start framing out, and you start looking at starting an analysis, is to try to take a step back and understand what the important things are that you're going to need to model to answer the questions that you want to answer with the model. So thank you for responding, everyone. But yeah, trick question of sorts. So stepping now, the next section is looking at where information comes from. So there's a lot of sources for data, and depending on where you are in design, or if it's an existing building, you might have lots of different data sources. But if you're in a design project, you're building a new building or doing a major reno, you likely will have drawings, some sort of plans, specs, hopefully a basis of design, sequences, maybe not. You might have an owner that's been in the building, a chief engineer. You might have designers that can help you inputs for the model. It varies widely, but a lot of times you're going to end up with gaps in your data, and this is sort of where it's critical to make sure that you're documenting the assumptions that you make, because you have you don't have all the data to fill in every question that you have. So you might be referencing other data sources to fill in gaps on your project. So looking at energy codes or prototype models, asking colleagues for a review on data, doing some digging on unmethours.com, or looking at manufacturers' data. So there's a lot of places where it might come from. Again, it's critical to document where that data came from as you're building out these models. So it can vary widely. So we'll do two examples of where data comes from. One, early stage, conceptual. You might not have much of anything. You might not even have massing. And the later design stage, where you actually have drawings, and you're doing a code compliance, where would you pull data from to populate the inputs for your model? So early on, let's say you have a conceptual design, you're trying to figure out geometry. You might not even have a geometry from your designer, right? They're still working on 3 different massing options. I have a project right now, we're doing the same thing, that, you know, the architect is working on a project with 3 different, you know, sort of program options, and we don't have one. So, you know, what we're doing is kind of looking at sort of these basic massing structures to kind of understand the you know, general programming of what's going to go in there. You might also be looking at, you know, sort of these very, you know, simplified blocks, which again, this can kind of be helpful, at least trying to get perimeter areas and like facade areas and volumes correct. Or you might just be grabbing a prototype model. So one of the, you know, one of the Department of Energy prototypes that's similar to your building type, and using that as the basis to start your analysis.
Sam,
So,
a
yes.
couple questions from Jose. What's the difference between energy codes and prototype models?
Okay. Well, energy codes are developed using the prototype models. The prototype models are, you know, intended to be sort of typical built to energy code. You know, for, I guess there's 16 different varieties of the prototypes, and those are used to inform development of future energy code. So they are the backbone of kind of doing these simulations and running the changes that are being proposed at the energy code level or the energy standard level to make changes for future energy code development. So sort of one and the same, but again, the code has sort of been driven by these prototype models ultimately. So and so what would your zoning look like as you get early on in these simple box models, you know, or a simple concept design, right? You might just have very simple perimeter core zoning, you know, using typical sort of rules of thumb, sort of a average 15-foot perimeter, you know, depth. Might have lots of, you know, different sort of shapes and geometry of what that might look like. But again, at this stage, it's probably very simple. You know, you're not trying to get too detailed because you don't have a whole lot of information at this point, right? So you're trying to just capture the fact that those different thermal zones are going to have different sort of load profiles through the course of the day and the course of the year. What about envelope? So there's a lot of places to look for envelope information. So again, if you're early on, likely you're just going to go look at energy code. So if you look at 90.1, you can kind of look at the requirements of chapter 5 and, you know, see exactly sort of what the minimum would be if you were going to meet prescriptive code requirement for building a new building in that climate zone. So that's one place. This is for opaque, you know, roof and a steel frame wall. There's also, again, system performance for windows. If it's an existing, you know, building and you're trying to figure out, you know, say an existing building that we're renovating, you might want to be trying to figure out what the existing window, you know, performance might be. You can also look in the back end of the handbook fundamentals. There's a lot of, you know, sort of data sets in here as well of the performance of glass, depending on the type of framing and what type of glass and airspace and such there might be. So that might be another place where you're making a, you know, making an input assumption based on, you know, the fact that you don't have data at this early point. So that could be another place to get data. Same thing goes for solar heat gain coefficients in the handbook of fundamentals. There's a, you know, a list for different window types. So yeah, you could be looking at energy code, so or energy standard like ASHRAE 90.1, or, you know, fundamentals. Prototype models also have, again, similar constructions and fenestration assemblies as you would find in the energy code. What about the amount of, yeah, the amount of windows? So in this case, you know, standard 90.1, if you're doing Appendix G, gives you a maximum window to wall ratio. Again, these are just based on the building stock of what we know is being built. And, you know, so that might be a place to start, you know, if you don't have any other information for it. There's a question about older buildings. So again, some of the older buildings, kind of looking at ASHRAE handbook and for fundamentals, that might be a place where you're going back. If you know you have an old building with single pane, you know, glass, you might be looking there to find what your, U factors are. There's not a great data set for that. So a lot of times, yeah, I mean, I'd say fundamentals is a good spot. There's also, what is the other? It's going to slip my mind right now. John, I'll come back to you on that. I've got a couple other, there are a couple other resources. I'll find them on the break and I'll get them to you. Yeah, sometimes we've done destructive testing too to figure out some of these things, or yeah, people might be, drilling holes to see what's in the assemblies of existing buildings. So, but I'll follow up. What about heat gains and schedules? So again, you're probably looking at energy code. You're looking at energy references. In this case, this is lighting power density, kind of by space type. So you might just say, well, we've got an office, we're going to use 0.64. As reference of what that looks like, again, if you're looking back at an older building, maybe it hasn't been renovated, you're trying to figure out what kind of lighting you should use for a baseline on an existing building. If you look back over time, you can kind of see what the standard 90.1 lighting power, and this is for an office. So, if it was built in 2000 and hasn't really, or at least it was following the 2000 standard for 90.1, say 2001 or 2004, you could use that lighting power input to define the lighting for that baseline condition. In terms of receptacles, this can vary quite widely, but there is, again, a lot of data sources out there, and you can kind of look at different variations, but this is just from the user's manual. This is kind of reference of actual measured data of watt per square foot average load for different space types. And then if you look more specifically into the fundamentals, the same thing, you can kind of look, and they've done this pretty heavily for offices because, there's been a lot of research time spent looking at offices of different setups of how people are working in offices. So whether you have a laptop or a desktop and how many screens and what level of usage. So you could be looking now at the fact that we have hybrid work schedules and things. You might be looking at sort of the light usage, and that might define your plug load density. So instead of that average of 0.75, you might be looking at something that's a lot less than that, particularly if everybody has laptops. So that could be also something that, when you're building the model, you're doing some sort of sensitivity about that in the model to see how much impact that has.
Yeah. Sam, there's a question about lighting power.
Yep. And the old building information we will talk a lot more about, but for lighting power, so the question about whether lighting power goes into heat gain, it depends on the type of lighting. So if you have a recessed LED fixture today, like your driver is up sort of above the ceiling in a typical office install, you're probably only getting 20% of that heat into the space off the front side of your LEDs, right? That's basically just conducting through your fixture. If you have, old surface mounted fluorescents, and your driver's actually in the space, like right at the ceiling, you're probably getting, closer to 80 or 90% of that heat load is actually showing up as heat, as gain. And if it's a, pendant type fixture, then you're probably getting 100%. So you kind of just have to look at the install, what type of lighting it is, and then how it's being installed. And then the other one is 2021, the most current version of the fundamentals. I believe there will be one released this year that will be 2024, but yeah, that is the most current one right now.
Yeah, 2025 will be the next fundamental.
Or 2025, sorry, I'm off by one. Yeah, every 4 years they update, so 2021 is the most updated. Moving on, other places to find inputs for internal gains. And again, this is a really good resource if you just kind of need to quickly populate lots of different things and you don't want to go dig and you haven't, you're not super familiar with, the different references. If you look at the BEM Cyclopedia, there is a great lookup table where you can pick your version of which 90.1, the type of data input you're looking for, and the building type, and it'll give you, a quick rundown. In this case, this is equipment power for a retail shop, right? So there's, again, slightly different equipment power densities depending on the area within that retail. So you could use that and take an average of those to figure out how much or apply those individually to specific zones if you're doing an early phase model. Again, lots of data options out there. Keeping track of it is very important to make sure you know where your data came from. And then in terms of schedules, also BEMcyclopedia has a really good list of schedules, again, based on the type of building and the end use profile. There also are very good schedules that come out of the user's manual for 90.1 that can be a good reference point. And then what about number of people? Again, you might have an idea from the architect, what the design occupancy will be for the future building. Even though it's early phase, you might know that it's going to be a 300-person theater. That's great. If you don't, you might be looking at other sources for that. So ASHRAE 62.1 has average occupant densities by area. The NREL document, again, that backs up all of the prototype models, has a lot of data in there as well in terms of the inputs that were built into all the prototypes, and it covers a pretty good list of space types. So a good place to start if you don't know the actual number of people. And then what do you do for HVAC when you're looking at a simple model? So again, you might have a package single zone, multi-zone, you might have fan coils. In this case, you might be testing different systems against each other, right? That's a very common use of an early phase model. So, you might be looking at fuel sources. You might only have electric to the site. You might have, fuel and gas and electric. So, understanding sort of what the goal is from the client, and maybe there's an HVAC designer on board and you're testing a few things. So, you might also be looking at if you don't have anything, right? You have sort of an empty box and nobody's on board. You might be going and looking at, again, 90.1. So if you look at 90.1 and you look at the different, space types, and in this case, they break it up sort of residential, retail, and then, non-residential. There are different, baseline systems that are applied, whether it's a PTAC in a residential, some sort of single zones, larger package multi-zones, or, larger central systems. So if you don't have anything else, you might just be modeling a baseline, ASHRAE Appendix G HVAC system to start with. Same thing goes for, yeah.
Luis asked, are the internal heat gains per person uniformly distributed in a simple model?
Yeah, they can be. I guess it depends on how many zones you have. You might know that you have, one zone. A lot of times, like the one we're doing now, that's a theater, it's got a theater and 2 support spaces. So that theater zone, we have very specific 350 people in that theater. And the other one is an office, and the other one is like a lobby corridor space. So you might have, 3 sort of use types. If you don't even have that much, if it's like an open office and you don't really know, you might be uniformly distributing your loads across the different spaces. It kind of depends. Good question though. So same thing in terms of equipment selections. You might be looking at efficiencies. A good place to start, again, is 90.1. If you're looking for a little more high performance, look at 189. You could also be looking at the future development of 90.1. So look at the 2022 standard, which is a little bit more improved than that. You could be looking at the advanced energy design guides or the net zero, achieving zero design guides. Again, just for ideas of things that you could be looking at. Again, if it's very early phase, you might be looking at lots of different system options and integration options. So good places to look to go find stuff. And again, BEMcyclopedia has a pretty good outline, and we'll talk more about it when you look at standard 209 of what actually what it actually looks like when you run through this process in a design design setting. Question of 189 versus 90.1. They're very similar in terms of standard. 189.1 covers a little more concerning total resources being consumed by a building. It is considered the high performance standard. Drew, I don't know if you have anything to add to that one.
No, I think those are kind of the best that's out there, but there are at least 3 zero energy guides and 5 on the 50%, but I think they all have an approach to that. There are a couple of questions before you go on. from Jacob. He wants to know whether BIM Cyclopedia is free.
It is free.
And
good and free.
Jose says, what a standard 189 cover versus 9.1.
Yeah, so 189 is more, holistic building resources. So it looks at water as well. It looks at materials. It was initially developed kind of looking at the holistic performance that a LEED project would require. But again, it's kind of I would call it a more energy efficient version of 90.1, but it's a little more holistic. It kind of leads into looking at these, net zero and 50%, reduced energy guides. It kind of is the driving factor towards getting some of those. So it's like a step up in performance, but it is a little more holistic.
I would add that it also adds a lot of green features to it that were set, as Sam said, baseline for LEED. So that was intended to be a lot of those prerequisites.
Right. Yeah. So if you look at the LEED program guide and you look at 189.1, you'll see there's a lot of similarity. The intent was that somebody, instead of a municipality saying, or a state even saying that they wanted to adopt a minimum LEED target to say you need to hit LEED silver or something, right? Because that's it's a very specific, you have to pay the program fees and do all this stuff associated with LEED. There's cost. They could just adopt 189.1, which has a nearly equivalent to achieving certain LEED rating. So that's the intent, is that municipalities could adopt it and say, by doing that, we're basically saying everybody has to build to LEED silver or whatever it may be. And we already sort of showed what this should look like, but I'm not going to ask everybody to write out their answers and submit them. But again, what factors would you consider when you're doing, again, early phase? We kind of showed this, but you don't really know much about what's going on in the building. Maybe you have an existing floor plate, from an old drawing. So what would you consider in terms of the zoning, right? And we talked about this before. You'd be looking at orientation. How much windows, if there's windows in certain areas, what the usage type is in that space. So that purple room, for example, is, no window. It's likely, either a bathroom or something else, IT closet or storage that probably has a different use type. So you probably want to isolate it. And then isolating perimeter versus, interior. So again, from a simple load, block model, that's kind of, you're keeping things high level. You're not really, getting way into the weeds on things. You're using a lot of assumptions, likely from energy code or existing building, information that you have or previous project experience. It's really, you're probably filling in a lot of gaps and you're making a lot of assumptions. So keeping track of your data that you're using in the model is very important at this kind of stage. Particularly when you get to the next stage, like say you go from concept to in the schematic or design development, and some of your input assumptions, you realize they change, you'll need to be able to document why the results of the model have changed. And if you have your assumptions documented really well, it's really easy to show, maybe the occupant density changed or the programming changed, and that's why the model results changed. So what about the alternative from, super simple concept, no information, to a code compliance model? So yeah, I realize my audio is getting a little funky. I'll sit a little closer to my microphone here. So for a code compliance model, likely you're going to have a full set of design documents, right? You're going to have probably more information than you need, and you need to suss out, just the information you need from it. So, but likely you'll have plans, on the architectural side. You might have a 3D BIM model. We can talk briefly about 3D BIM models, but generally you're going to have layouts that are showing all the different space types, the use functions, different assemblies. You'll have elevations that are showing where your windows are, the types of windows, the potential types of assemblies. So different, envelope and construction assemblies. You'll have section drawings. So these are helpful, again, to show, again, if you have a plenum return, for example, or, built up roof assemblies, for example, and you want to see exactly how much insulation you have at the roof. It's helpful, for those purposes, all helpful to show interior sort of ceiling heights. If you're placing, say, sensors for daylighting, it'll give you an idea of how big your interior zone actually looks like. So there are workflows, and somebody had asked earlier about this in terms of going from, well, maybe not directly, but going from one software to another, or from one purpose of a model to another. There are some softwares that do this well. I still think a lot of architectural models that are built, for a BIM model, a building information model, are likely too complicated and have too much information than what you need for a building energy model. So a lot of times you end up simplifying. I know there are workflows that work well for doing it. I'd say I haven't had a great experience in my career doing that. We end up generally rebuilding a model, even if we have a 3D. But there are workflows to export basically the geometry from a BIM model into a software tool. And some software tools have, integrated analysis capability as well. So depending on the level of accuracy and what you're trying to get at, you could be able to do the simulation directly in the tool. Richard, is Autodesk planning on providing update support for GDXML supporting? That would be a good question for Autodesk. As far, we do some beta testing and other things for them. I don't know if they're planning on providing any further update on export in that format, but it's certainly worth reaching out to them to know. As far as I know, they're not. They're planning on really using their internal capability going forward to be able to run simulations directly from Revit. So, but you never know, it might all change. Good question. So moving on for this compliance model, where would envelope components come from, right? We've got drawings. In this case, you might also have specs and submittals. But you might not have all the information you need, right? So this might be a typical sort of elevation of what you get. You might have, a curtain wall, a metal panel, and a GFRC panel, right? And they give you sort of the location on the building, so you could do takeoffs. You could figure out how much area of each type of assembly you have, which is helpful. You need that. But it doesn't really give you any information about the performance, right? The mass of those assemblies, the thermal resistance of those assemblies. So you probably need to start digging. And in this case, you'll probably dig down and start looking at section drawings, right? In this case, this gives you a much better idea of actually what's going on with your assembly, right? So you've got, steel studs, you've got insulation in between your studs, inside of a secondary sort of rain screen type system. So again, from that, you could likely go and you could look at Appendix A and 90.1, and you could look up, performance of that assembly. And sometimes you might also have, an energy code filing, and that energy code filing might actually have these things already pre-calculated for you. So if there's an envelope consultant, they might have already determined, what this could be. But likely you will be calculating what that looks like, and so you're probably building up a set of layers, and from those layers you're creating assemblies. Another good place to look, and again we're going to give you a lot of resources in the next day and a half, is the thermal bridging envelope guide, and this is developed by Morrison Hershfield in British Columbia, but it has a lot of different assembly types and different sort of insulation locations and different makeups of fairly typical assemblies. And I think there's like over 100 different ones in here, but they give you for different sort of stud spacing, they give you the nominal 1D versus the total assembly, right? And so it's helpful to see they've already done this derating, they've done a lot of testing, and they built what are called these 3D therm models to figure out what is the actual true performance of these different assemblies, depending on whether or not they're thermally broken or they have thermal bridges and things like that. So again, another great resource. If you don't have calculated data, you could go and just pull these off and say, yep, it's non-thermally broken. We have performance of here, and then you could reference this guide, right? And that's an easy reference point to use in a compliance model. Again, also go back to Appendix A if you're looking up, example for a steel frame wall that's got continuous exterior insulation. You can look up how much exterior, how much you have in the stud, the depth of your framing and pull the value directly off of here. And then starting in 2022, the ASHRAE standard actually requires you to document thermal bridges. And so this gets, again, a little more complicated, where you have to actually look at linear thermal bridges, which is a length, and point thermal bridges, which again are protrusions, basically where you have a structure that goes through insulated assemblies. Not going to go through a lot of it here, but again, it's important that if you're looking at a newer version of the standard, that you need to document compliance with these. And certain municipalities have already picked this up as well, where you need to document thermal bridging. So there's a whole set of factors that are included in the 2022 standard. So again, if you want to be more accurate about the actual performance of a wall, you can look one version forward on the standard. And then in terms of glass, again, you might get NFRC data, which gives you, this is for a specific curtain wall. So this is a tested assembly value. Very easy, you just input that value. You might be using a second software. So this is, I mentioned before, there's a software from LBNL that's called Windows, where you can actually put in different glass types and different coatings on the individual surfaces. You can build up multiple layers, double pane, triple pane, what type of gas, the type of frame, and it will export assembly values for you. So you have the overall U factor and solar heat gain. It also exports this spectral data. Again, that is a little more accurate if you're accounting for the fact that you have large panes of glass that might have different heat gains throughout the day based on solar position. So again, depending on the level of accuracy you're looking for in the model, you might just use a single U factor and a single solar heat gain. Otherwise, you might be using these spectral files if you need to be more accurate for the envelope. What about lighting and internal loads in general? So at this point, likely you will have lighting plans, and we'll zoom in on a specific a couple spaces here. So again, this is just a reflected ceiling plan out of a architectural set. So what you normally will see, but what you'll end up getting off of a drawing is you'll get the fixture labels. You'll get a lowercase letter that has, again, if you're familiar with these, this is, sorry to repeat, but you'll have a circuit label, which is usually a small notation of a letter or number, in this case A, that shows which circuit those specific fixtures are on. You might have sensors, in this case aux sensors. You might have control switches on panels that'll tell you actually what kind of switching you have on the wall. But again, from that, what you can end up doing is counting up fixtures, put wattages to each one of those fixtures, right? You'll find out what type they are. Again, this will be helpful for determining how much heat's going into the space versus how much will be going into, say, a return plenum or a plenum space, right? Whether it's a recessed, in this case, both of these are recessed. But again, the very typical fixture schedule will give you, the type of fixture. It'll give you the wattage, and from that you can calculate, the watt per square foot that you would use in the model. And then the control factors, again, in 90.1, there's a table of how you account for control factors, whether it's aux sensors, vacancy sensors, daylight. So again, once you have all that, you have basically everything you need for those. Drew, was there a question?
Yeah, Asia asked, what resources, tools can we use for total U value?
Sure. In terms of tools, I'm going to go back briefly here and just show this screen. So what Morrison Hirschfield has done in their bridging guide is they're using a tool. This is called Therm. And so what they're doing is they're building up the actual components of the individual wall. So they're putting the metal studs and the chipboard and the insulation layer and the exterior, panel condition, whatever it is, and you run it this 3D simulation to determine performance. So again, if you're in the envelope consulting world, likely that would be something you're doing. For the most part, for energy modeling, you're just going to go to the tables and look up, based on the stud spacing and based on how much insulation is in the cavity, you're just going to look up, the overall numbers. And that's the same point here if you're looking at, Appendix A of 90.1. For steel frame, wood frame, you kind of just look up framing type, insulation in your cavity, and continuous exterior to come up to values. So but therm really is the big one for doing assemblies if you're going to be doing more complex assemblies. So I would use the Morrison Hirschfield guide as the basis, and if you don't see it in there, then it might be something you would need to go model separately. Good question. So back to lighting, again, you might have everything you need. So from watts and number of fixtures, you can determine your watt per square foot input that you would put in your model. What about the rest of the internal heat gains? So again, we talked about a lot of these. Some of these occupant density might be on your drawings. You might know how many people are going to be there, but you might need to estimate that if they haven't actually given you occupant density. So that could be various sources. Same for plug loads. You might, they might not give you a number. I haven't really seen a set of drawings that says here's the plug load or small power allowance for the building. So you probably have to go look something up. And then schedules, again, for a compliance model, you really just want to make sure the thing is that you're using schedules that are realistic. And you have to use the same set of schedules in both models. So as long as you're not varying the schedule types, you're in compliance with, following the guideline to show, compliance for energy code. So.
Yep, Sam, I would add that the electrical load, the allowable load that's on the electrical drawing is probably 5 times what the actual load will be, just
right.
partly because for that. So don't take just what the electrical engineers put on there, because that's not what you're going to see in operation.
Right. So yeah, they might have an allowance of say 6 watts a square foot or something. Right. That's a tenant allowance, just on their lease. But if you go back to the previous resources we were showing, if it's a typical office, you're probably looking at half a watt a square foot, maybe 0.75 watts a square foot. Data center or trading floor obviously might have different numbers, but there are good resources out there. And I would say, look at the fundamentals as a good option for that. You can also look at the Title 24. There's some very good data there. There's also good schedules there as well. Excuse me. And what about HVAC? So in this case, you probably have a set of plans, right? And you have schedules, you have riser diagrams. So, but in some cases, you might not have enough information. So this happens quite often where you have, I will show a great example of it. You have a, packaged sort of rooftop equipment schedule, right? And the mechanical engineer says you have everything you need to build your model, like here you go. And you start looking and you realize like maybe there's some stuff missing. So, you always have to look through your notes to see like, okay, we're marked 1, 2, 3, and 4. So we've got DDC controllers, we've got an economizer. Okay, good to know we have an economizer. We have a power exhaust that's here, that's 2 horsepower. You have your outside air CFM, you have your total CFM, you have static, pressure, you have your cooling coil performance, the efficiency, again, rated of your equipment. Okay, everything looks pretty good. You've got a couple existing units that you really don't have information for, right? So you might be having to fill in some gaps for all of those based on, older version of ASHRAE or something else. But does anyone see, put this out there just to see, is anything missing specific off of this first unit AC1 that you would need for the model? There's like one very glaring thing that is not included. And I'll hint, it has something to do with airflow, right? That you have an external static and you have a CFM, and you have a total electrical. But nowhere does it tell you actually the size of the fan power. Yeah, so I think people got it there. So, you actually don't know how big the fan is that's serving this unit, right? So what you might have to end up doing is, right, go look up this model, right? Or you might have to ask them for the selection sheet for the specific piece of equipment. So it's not as simple as just going to the schedule and picking it up. A lot of engineers will have, the fan power on here, and they likely will have a brake horsepower, which is what you need for the model, right? Instead of the full load on the motor. So good for everyone. So there's a question, the note for number 3, that is the power exhaust. That is only 2 horsepower, but it doesn't actually give us the main supply fan horsepower. So good catch on that. But yeah, we're still missing total fan in this example. So again, you might have to be, digging for more information, even on a compliance model where you have a full set of drawings. In terms of setting out zoning, in this case, you'll have a good set of plans, hopefully, that'll show you, distribution ductwork. In this case, it's a little bit easier. We'll run through just a quick, example here of what we have. So you have, supply shaft that's coming down to main sort of trunks. You have individual VAV boxes. You have distribution, final distribution ductwork. In this case, you don't have specific returns. Yeah, so you're not seeing return, but you're seeing everything on the supply side on the ventilation. And in the background, you can kind of see we're overlaying a little bit. It's that same zone that we were talking about before, the same sort of system that's got this big perimeter zone, right? Where you can see the thermal zoning is kind of set out against this envelope. And you'll see that there's thermostats shown here as well. So, right, you might be looking for which VAV boxes are on which thermostats. That might help you, dictate, which VAV boxes should be, on the same zone, for example.
Sam, excuse me, Jose noted that the horsepower was on note 3.
Yeah, note 3 was only for the power exhaust, right? So that's just
and
Craig, CFM and static. Thing is, we only have external static, right? So we don't have total static. So good point. If we had total static, then yes, you could determine fan power from that. But in this case, we only have external. So again, still missing a critical piece of information of modeling what we need to deal with the fans. And it also doesn't say how the fans are being controlled, right? We don't know if it's a constant speed fan controller or if it's a variable speed fan controller. So that would be, something else to understand. There's a question there about exhaust fan energy considered unregulated. Exhaust fan is not considered unregulated, but again, total, if you look at Appendix G, the way that it accounts for fan energy, it's total system fan energy, right? So you have to account for supply, return, exhaust in your total calculation. So it is not considered process. If it is, let's say if you had a kitchen that is doing exhaust, right? That is a process exhaust system, so that would be modeled neutrally. But in this case, this is part of this package system, so you need to account for it in the total system fan power. For the building performance factor, yeah. So your exhaust fan energy still ends up in there if it's part of your package system. So Appendix G is part of 90.1 and not Title 24. So Title 24 has a slightly separate approach for dealing with fan power, but they still will have you account for that exhaust in your total fan system performance. So what are some other things that you might gather from the mechanical drawing? So in this case, you might be looking at whether the VAV boxes have reheat in them. So in this case, they have reheat. You might also be getting the minimum flows on your boxes, right? So you need to know what the minimum turn down is on your VAV boxes. A fairly critical item, have a very large impact on energy consumption. So in this case, that first box, gives us a minimum of 325 CFM and a max of 1404, right? So that will give you, the minimum total airflow of 23%, right? And then if you look at heating, you'll say in heating mode, so that's say cooling mode, you have 23%. In heating mode, that's a 40% flow. So those give you two inputs to the model that are fairly critical to how the VAV system is going to run. So quick exercise, and then we'll keep moving. What is the lighting power density for this space? So you have everything you need in here. There's 4 F2s. You got them up here. You've got your luminaire schedule, and you've got the F1s. And you have your total dimensions. I'll give everybody 1 minute. Quick back of the napkin. All right. We're getting some answers. All right. I think a lot of people hit on it here. Yeah, so the lighting power density here would be 0.6667 watts per square foot. So that's good. And so the total is, multiply your F1s, there's 14 of them, times 50, your F2, there's 4 of them, times 25 for total watts of 800 watts. And you divide that by your total area, which is 1,200 square feet. So for comparison, if you're looking at, an open office category, this type of space, if it was open office, would be a 0.6. So, right, so this design would be a little bit above and beyond the minimum code requirements. Thank you, everyone who responded. Next thing is just a discussion, and this is, I sort of mentioned it a little bit before, but about keeping track of what you've done while you're running through these models. But what are some things you could do to make sure that your inputs are reasonable and accurate? So how would you make sure that the data you're putting into the model is good data, right? That's kind of, we sort of started out with that. We'll keep circling back to that the inputs into your model and the results out are only as good as keeping track of what you've actually documented and what you've assumed, right? So if you put junk in, you're going to get junk out. So the best educated guesses that we can make, or whether you have design documents, making sure you translate those design documents correctly. So some things you might consider here is reviewing your input sheet with the design engineer and the owner and the architect, right? Have somebody else look at your model. So if you have in-house, if you're working in a team, have somebody else do a QC, right? Don't have a third party basically look at your and we'll talk more about some other things as well, but make sure you look at your outputs. Make sure that like for example on an envelope input, if you calculated a detailed sort of U value, make sure that what is coming out of the model is actually showing the correct U value that you've calculated. Other things, compared to other previous models you've done, benchmarks, look at CBEX, for example, and other things like that. So, but again, keeping track of what you've put into the model is very important, where the data came from, because it'll help you go back when there's questions to be able to answer those questions. All right, we've got one more quick session and we'll take a break here. So I think we've got about 20 minutes, maybe a little over 20 minutes, and then so right about 2 o'clock. So Craig, compared to benchmarks, that's a great option. Take pictures of nameplates. Yes, absolutely. Existing buildings are a whole other animal, right? In that, you have a piece of data that is a piece of equipment that's there. And you could have way more information than you need, but keeping track, right? It's very important to keep track of what you've put into the model, because it's very hard to go back if you didn't document it and figure out where stuff came from, or if you're passing it on to someone else or having somebody do a peer review. It's much easier if they know where all the data is coming from. So last section before our break here will be what happens when a simulation actually runs, right? So we've built this model, all these inputs, and Drew will talk about weather briefly before the end of the day. But what actually happens when you run, like when you press the simulate button on your tool, whatever tool it may be, you kind of need to know a little bit about what's under the hood, because certain tools and certain methodologies will help describe certain systems better, and they will more accurately calculate the results of those systems better than other tools. So it's kind of good to know what's going on under the hood. But generally what's happening is, and this is for all simulation tools, is that the sum of all of your internal heat gains, your envelope heat transfer, and your infiltration are getting translated into a combined load, right? That'll show up in a zone as a heat load or a cooling load that needs to be met by HVAC. That HVAC system receives, that load data, adds in the ventilation at this point. So, whether it's cold air or hot air outside, and that HVAC model runs to, meet those heating or cooling loads, right? So what comes out of that, you have energy out of the zone model that is, your lighting, plug loads, all of your sort of zone level energy consumption. And out of the HVAC model, you have all your HVAC related energy consumption. So fans, pumps, and then all your primary equipment. And that all gets summed up to get total consumption, cost, and emissions, right? So very, very high level, but that's really what's going on, right? Is you've got kind of at each time step, you're doing the same calculation for every time step through the entire model. So for 87, 60 hours. So what happens with internal heat gains, right? So I mean, again, going back to what we've talked about before, is that you're going to have convective, radiant, and latent loads that all need to be accounted for. So you've made an input for each one of these values in the model. You've got heat that's coming either in from your windows or escaping through your windows, the same through your walls, your roof. So at each time step, the sum of all of those get added up, including your infiltration, right? So you have a load, whether it's a heating load or a cooling load. And again, if it's hot inside and cold outside, you might have, almost a neutral, load on the inside. But that's what happens at each hour. Yeah, and again, the opaque sort of envelope and fenestration, accounts for the weather that is outside of your building, right? So there's an external component here as well that is determining the amount of heat transfer that's happening through your opaque pieces. So if there's an HVAC system, and again, you could just, there's different ways. If the HVAC system is off, for example, scheduled off for that, that will just increase the temperature and humidity in the room for that hour, right? Or if it's on, that load then will get passed to your cooling coil, your heating coil, whatever it may be, as a feedback mechanism to understand how much energy is consumed by reducing or increasing to meet that load. So again, a little theoretical, but this is sort of assuming, again, a fully mixed zone. There are ways to account for stratification within zones, particularly if you have an underfloor distribution system, but not for the purview of today. So that's sort of high level, right? You're taking all of your internal gains, all of your envelope gains, you're summing them up and passing that information to your HVAC, and then determining what the HVAC response is to those loads. So there's two main ways that these are, that a simulation engine is doing this calculation, right? So one, which is on the left here, which is response factor, weighting factor method. This is, again, considering conduction through your envelope. That's accounting for response factor. So this is basically how much heat enters the outside wall at each hour. So again, this accounts for the amount of mass that is in your wall. So heavier mass walls will slow down the amount of heat that enters at each hour. And it accounts for a response factor over a certain number of hours for that heat to actually enter into the space. And then once it enters the space, there are, again, for all the other loads, including envelope, there are weighting factors. And those are simpler, but similar to what the response factor is, but it's accounting for the actual thermal mass of the total interior space. Since now the heat has entered or has left, you have a load in the space now. So this accounts for the mass of furniture and the interior walls and the roof and the floor in terms of how long it takes for those loads to show up as actual loads on your coils. Most softwares will do a custom weighting factor, again, depending on what you put in for furniture in the space. So that's a fairly critical thing you need to do. This is generally pretty fast. And what it does is that each time step, again, you're calculating this for every single one of these inputs, right? So you have an 8760 list. It's fast, very accurate. Heat balance on the other side is looking at a general heat gain, and it's a heat balance where actually you're balancing temperature of each of the surfaces inside, and it's doing an iterative surface and air sort of heat balance, right? So the difference to this is that you can deal with surface temperatures. You're also accounting for radiant heat transfer in this case. So you're, again, it's similar. You end up with a similar result. You're getting, an effective load at the end of each time step. but it also does account for radiant. It takes a little more time for this to run, obviously, because you're iterating. It's not going to be a single just summation calculation. You will iterate to find it. Again, and it depends on what you're doing. If you're looking at a system that has radiant heating and cooling provided as part of it, of like a radiant sliver system or something like that, you might want to consider using a tool that uses heat balance method versus a response factor methodology for load calculations. How can you account for stratification, Carrie asked? So again, there's a few different ways. Some tools do it a little bit differently, but if we look at this example, in this case, you've got a plenum zone. If you had, for example, if you wanted to account for a tall space, you could essentially have an intermediate zone. Again, if you consider this to be a tall, you can have an intermediate zone between the two that would account for, a lower zone and an upper zone, and you could isolate heat gain, say from the people and computers to the lower, and you could put the lights in the upper zone, and that would account better for stratification. Same goes for like an underfloor system where you might have a colder mass of air or a hotter mass of air below the occupied level. So there's different ways, and you could have, I've seen models that have, 5 or 6 different levels of stratification for very large envelopes. And some softwares will also do some interior CFD to account for, heat transfer between the different stratified zones. So different approach, pretty technical when you get into it, but again, you can just basically create zones that are stacked on top of each other to account for them. Then the next question, Kate asked, what does DO2 use? DO2 uses the response factor weighting factor method on this side. So again, y-equals runs fairly quickly, and yeah, compared to the one on the right. So the right is more typical. So that's for Energy Plus, as an example, it uses heat balance. So again, what exactly happens? We've calculated all the zone loads; those get passed to the HVAC, right? And you have the calculation for each one of your coils, or whatever sort of heating or cooling equipment you have, your fans, pumps, and that gives you energy consumption. And a lot of tools now will give you outputs, so it'll tell you what the flow and temperature was, before and after each one of the coils, or before and after the fans. There's a ton of data that comes out of every simulation you run, and you might not need all of it, but most of the tools these days have a lot of data that you can collect, and particularly if you're running the heat balance method, you get a lot more data about where loads are coming from and about thermal comfort, for example, which you don't really get that information when you're doing a response factor weighting factor tool. Another big variation between the two sort of calculation methodologies is how load and system simulations are completed. So for example, in the response factor weighting factor, using DO2 as an example, the loads are calculated for the full year, 8760, and then that is passed to the system, and then the system is run based on that results from your 8760. The system, so the HVAC systems then run against that 8760 hour. So it's basically sequential, it runs linear, there's no feedback, right? So if a zone is getting out of set point, it's going to continue to get out of set point, but every time step is basically using a constant temperature starting point. So fairly fast, again, linear in that sense. There's no feedback. So if you have a lot of unmet hours, it's a little bit harder to figure out where they're coming from, but again, it's pretty fast to do that. Whereas if you look at Energy Plus, it's a simultaneous, right? At each time step, the load is calculated, it's passed to the system. The resultant load that's being met by the system passes back the resultant temperature and surface temperatures back to the loads to calculate the loads for the next step. So in Energy Plus, you might have non-convergence because you have this feedback loop. Whereas say in DO2, you would just have hundreds or thousands of unmet hours, right? It would just say that consistently you can't meet it. In this case, you might not actually converge. So this, again, is very helpful on the simultaneous side to understand where loads are coming from. It'll also, show you if there's rooms that are getting, or thermal zones that are getting out of thermal comfort fairly quickly. It'll end up, kicking you out of the software. So again, it takes a little more time to run the simultaneous ones because you end up having to converge, do an iterative approach for every single time step. But it can be more accurate depending on what you're trying to get to. So question, we'll just quickly try to move along here, but for an example, if we look on the one on the left, we'll just do the cooling load day because it's a little more easy to understand. Which of the results, either the red line or the blue line, would be considered a space that has high mass? And this could be both interior to the space and your exterior wall. So if you had a high mass building compared to a, say, low mass building, which one would be the high mass? Yep. Okay. Yep. So I think getting responses of red. Yeah. So in this case, your envelope and your interior walls would be absorbing a chunk of this, considered cooling load, right? So saying it's hot outside. So it would slow down the amount of heat that transfers through. And again, and some of that heat would end up being re-radiated back out into the environment, depending on the day. So yeah, generally with a high mass space, you're going to end up with a lower sort of profile like that. Cool. All right, last section, and then we'll hand off to Drew, which is, again, we're kind of starting at the top. We're going to slowly get more and more into the weeds. But so let's say you've done that, you've built your model, you've run it. What do you actually get out of your model? What results do you get? So hopefully you get information that answers your questions, and it helps you debug your model or verify your model, depending on what you're trying to use the model for. But in general, you're going to be getting annual energy and demand numbers. You'll get monthly numbers summed up. Most tools will do that. You also get whatever you simulated at the time step. So most commonly that's at an hour, but depending on the tool, it might be sub-hour data as well. And if you put in your utility rates, you'll get monthly and annual costs. So in this case, this is electric gas. So this might be an example of what you would get out in terms of electric gas. You might also get, a site EUI month over month. That kind of gives you an idea of, month over month where your energy is being consumed, right? And as a function of total electric and gas, like what's the ratio of electric to gas consumption? So good way to check seasonally, does it make sense? So kind of high level. In terms of end use consumption, when most softwares will put this all out for you too. It'll tell you each hour and monthly and annually how much are each of your individual building systems consuming. So your lighting systems, your small power systems, your fans, your pumps, your boiler, your chiller, cooling tower, domestic hot water, right? So all of that is getting calculated. The energy use is being calculated for every time step, and that's being summed up. So what might this look like in terms of, presentation? You might have an end use breakdown in sort of a pie graph. Again, to look where your energy is going. Similarly, it can be, presented in a bar graph to understand month over month. Again, depends on what you're trying to convey, what information you're trying to show. So you can also go down one level further and start looking at what's going on specific to your system and zone level loads, right? So you could be looking at what is the load on your cooling coil at every time step, your heating coil at every time step. What is the flow on your boiler, circulation pump? What is the flow on your primary chilled water pump each hour? You could be looking for the total internal loads, sensible latent loads. And what might that look like? You might be tracking the cooling coil load over the course of a season and the heating coil load over the course of a season, or the course of a year. Again, just different ways of presenting data. And then if you go all the way down into individual, hourly or sub-hourly data, right, you can start looking at much more specific data. So you could look for a specific hour. You could say, I want to understand, is my economizer working, right? You might look at the damper position, the mixed air condition, and your supply air and return air, right, to figure out, is that mixed air what it should be? Should it be economizing for that time period, right? So you could be also looking, as the other data point that's not shown here is, the outdoor air condition, right? Is that within the range of your economizer activating? So, and then, yeah, again, the same thing, flows temperatures for all of your secondary and distribution system. So again, the volume of data is quite high, and zone level temperature humidity controls. So what might this look like? You might be looking to make sure your thermostats are setting back at night, which looks to be working very well both for your summer and winter. And then you might be looking, seasonally to see what happens in shoulder season. And you see that it's kind of switching over between heating and cooling between your seasons. So other ways to visualize data. So again, information that you might be looking for to get out of this, again, cost, total electric gas consumption. Again, these are fairly straightforward: steam, chilled water. Peak loads on equipment might be something that would come out. If you're looking at thermal storage, this is kind of a good, place to go in and get your hourly data, right? To understand what your heating and cooling loads are, to help for sizing of a thermal storage system and what you would need to shave off, peaks and how much storage you would actually need. And then what sort of information, again, if you've been documenting this fairly well as you're going through the process, right, you're going to have this summary of inputs. So you're going to have, zone level inputs with all of your internal gains. You'll have envelope performance, all your HVAC equipment, related parameters. And then on the outputs, like we said, there's kind of this fairly large list of things. And again, if you're debugging and you're trying to figure out what's going on, there's usually sufficient information to understand exactly why you're getting certain temperatures or results out of a model. But again, it's a fairly big list. So back to the sort of, more theoretical, just put that out there and then we'll try to jump off for a quick break here. But, what's the optimal window area? If someone was to ask you what's the optimal window area, what sort of information would you need to know in order to answer that question? Right. So what sort of information would you, get out of the model to help you answer? And there's no right answer again for this, but it's kind of just thinking of, how do you frame these analyses? How do you, think about the end result and kind of work that backwards in terms of how you start framing your analysis and where you're going to start with your analysis. So yeah, so so you'd be looking at, in terms of inputs, optimal window area, all of the performance of that, right? So construction, orientation, I think people are hitting it on here. And then answers of what output information would help you, and it sort of depends on what the result is and what the client is looking for, in terms of their goals, right? So you'd have to kind of think about that, but maybe it's cost, maybe it's carbon. So I think Andrew hit it on the head there, could be thermal comfort, right? You might be considering how, if you have big private offices on the exterior for this high window area, are the people going to be comfortable in there, right? That could be something that you need to test out of the model. So daylight factors, yeah. So, I mean, again, it sort of depends on what you're trying to answer using the model, right? And I think that's fairly critical, is you got to make sure that that is very well established before you start jumping into this. So, and then a couple last things. So what does BEM look like over the lifestyle, right? We talked about this pre-design, we talked about this sort of compliance model, but there's a lot of stuff sort of in the middle where you're kind of helping make decisions. You might have more robust models that you're building as through schematic and design development, and then you're ultimately ending up with this compliance model. And a lot of times what we get called and asked for is this value engineering. We've done all of this, and at the end of the day, they want to change insulation, or as of today, a lighting fixture that they want to change by 2 watts, right? So there could be a lot of reasons that you end up, opening a model back up. But again, the most common ones are these compliance and green building certification ones. And what does it look like in terms of, comparison when you're doing, say, this compliance model? Really, all you're saying is that you have a proposed model that's built to your specifications and drawings, and that needs to be less than, and there's a lot of metrics for what that could be, than a standard design or your baseline code design, right? So that could be 90.1, which we've talked about a little today, or IECC, which is a cost basis, although there are permutations and allowances now to use source energy, site energy, and carbon. So there's a lot of options. And if you look at California, for example, Title 24, you need to use the TDV and source energy calculations. So again, it kind of just depends. And again, we sort of talked about both of these already, but there's building energy modeling that's using to help design. So the early phase, kind of looking at options for simple box. We'll talk a little more this afternoon about it. Optimization and value engineering, and then there's all the sort of documentation pieces. We talked about code compliance and lead. More often than not, the utilities now are asking for models when they're doing documentation for utility, rebate programs and things like that. And obviously for 179D and 45L, you have to have models built for those as well. And then you can also look past, and we'll talk about this tomorrow, past the actual, design. You get into construction, you might be looking at, VE like we talked about, but in operation and retrofit, there's a whole separate use of building energy modeling when you're trying to evaluate changes to an existing building, or you're trying to evaluate why a building is not performing as it was designed and the original design model said, right? So that could be, look at real utility bills and be like, how far off were we and why were we off? Or it could be, we want to make a chiller change or a facade change to an existing building. So, and we'll leave this for you for break, and you can type in. So if there was a project that you were involved in where BEM could have been beneficial, but it wasn't used. So if there was a decision or something that happened on a project where if you had a model that could have proven something, always interested to hear people's experience with it. So, all right, and with that, we're at 2:05. Drew, what do you think about a break? Should we do about 7-8 minutes?
Yeah, I think we ought to try to be back by what, 12, well, it's 2:06 now, 13, 14 past the hour.
Yeah, so let's say, say 7-8 minutes from now. So we'll restart at 2:14 Eastern time. So quick break if you need to grab snack, drink, whatever. We'll be back.
Okay. I'd like to go ahead and get started in part two. Drew Crawley here. I did see some answers to Sam's last question. Jose said a client wanting to replace like-for-like HVAC units did not work because the load and design was almost twice from the unit he was using. BIM could approve the need to use further load. And let's see, trying to, Andrew says early design decisions not to include active cooling. Project was in Northern Canada. Building ended up with a few zones would overheat due to solar gain. Could have better predicted and prevented this through the use of BEM. And Kara said to reduce the many value engineering iterations that continued throughout the project. Sam, Richard also asked, do you have any examples of unregulated energy use besides receptacle usage for performance cost index?
There's a long list. Basically anything that's not considered regulated, right? So it's all the small power loads. But the other ones that are generally excluded are like vehicle chargers are excluded, kitchen equipment, data center, IT loads.
Just about any process.
Yeah, anything that's sort of process related, right? So any of the fan energy that's associated with, large processes things. So a lot of industrial stuff would be included as well. Anything that's not covered under sections or chapters 5 to 10 in ASHRAE, right, would be considered non-regulated. So
yeah, it winds up being a lot in many buildings. particularly as buildings get more efficient. But,
Yeah.
And one last comment, Sean said decision on whether how much to electrify also is a
Great.
way
Yeah, those are all great examples of how to use BEM. So
yeah.
thank you.
Okay, so now we're going to start on who uses BIM or who does BIM. And so get things going. And it's pretty much everybody who's doing anything with building regulation, from architecture, HVAC, consulting, energy service companies, energy performance contracting, policy, utility, government, research, and so on. So it's a broad range of people that are doing BIM today, and they do it for different reasons. But you'll find it could be somebody with an AE background or mechanical engineering, other civil engineering, architecture, physics, computer science, etc. So lots of people do have that capability, and they come with different aspects of what they're interested in for using them in general. So it may be somebody that's working with an architect or a designer or sustainability, or they could, work for any or all, or they could even be separate. One of the things they're doing is related to building performance. They probably are the key player in this, being able to get information from each of the participants in the project, as well as having their pulse on everything going, providing impact on major design decisions, and understanding each player's role in this as well. And probably most importantly is they are watching as design changes are posted and are learning what's going on. I had a project I worked on many years ago, and we watched the design changes, and the architect neglected to tell us about the data center or the cafeteria until we got well past schematic drawings. So the energy use changed over time, but we were able to show that they were still on track, meeting the target for that particular project. So what does an energy modeler do? Well, they are primarily a team member working to determine what it is we're trying to achieve. What are we trying to do with analysis? And also helping to select alternatives that can be evaluated. They develop an analysis approach and a QA process. They are responsible for getting the inputs, building the models, running simulations of the alternatives, doing quality checks on the results, making sure they make sense, and evaluating the results for insights, because that's kind of the key. Presenting data is interesting, but it's not really, doesn't tell the architect, the engineer, or the owner what it is they're supposed to do with that. And that's that effective presentation results is really key. And then throughout the project, helping stay on track to meeting any goals, objectives, whether they're energy or cost or even carbon today, and help people understand how they can do that. And that's not just a one-time thing that happens continually. So lots of different job titles. So it could be somebody who's an energy analyst, or a consultant or sustainability designer, but it also could just be a mechanical engineer or other role, or even an architectural position. So there's a lot of different people that are involved in doing energy modeling, but it's important to understand they're all focusing on the same thing, but maybe others. So why are modelers so cool? Well, first, they really are the ones that have the big picture view of building performance. They have the details, but they also know where it fits into the broader process. They can look at the building as a system, how the systems interact, coordinate with other team members. And I think that's particularly important so that team members can understand how their individual contributions can affect that, but they also can show how it affects other team members and other parts of the design. And if they're trying to do low energy, low carbon design, they really are the way to be able to do that, to show that we're making that, meeting that goal or on target to do that. So we've talked about a number of tools, whole building simulation tools, Energy Plus, eQuest, the DO2 family, Transys, Trace, 3D, Carrier HAP, TAS, IESVE, Open Building Designer, and Autodesk GBS and Symergy are examples of some of the most common tools used. There is a building energy software tools directory, which has a look at many of those. It's kind of a one-pager to be able to do that. But some of the tools that you may want to do, and Sam has already mentioned a number of these, window thermal optics coming from Lawrence Berkeley Lab. They are tools to be able to look at a detailed model of a window, the optics properties, but also therm can help you look at framing and doing that. And one of the interesting things is because these are used in actually putting some of the NFRC labels together to be able to put that, so they are trusted in the industry as providing accurate. Climate consultant, I'll show you an example of that a bit later. Klima, there's a CBE thermal comfort tool, Elements, DView, etc. And some of these tools will let you look at climate data. Some of them are looking at other aspects. The comfort tool, obviously. So there's a lot of different ways of getting those, and you may find these useful if you're trying to focus specifically on the fenestration or climate, looking at ways to take advantage of those opportunities. So there are kind of two parts, and what you'll see is that you may have an engine. You may have one of the DO2 engines, such as DO2 1E, 2.2, or 2.3, and they'll have different interfaces for that. Energy Plus, you see, has quite a number of different interfaces at this point. HAP, specific to the Carrier product, Apache, specific to IESVE, and Transys. So Transys does have an engine, but it also has an interface for that. Each of them has strengths and capabilities, and as Sam talked about, one of the biggest differences is between response factors, weighting factors, and the heat balance method. There are other tools out there. I'm not mentioning there's some of them from Europe that are dealing with more of a matrix solution. It's just a different approach to the heat balance, but it does take into account all the interactions quite well. But computationally can be quite intensive. So let's look at an early design project and see what we're doing. So this is a public library in New York City, 18,000 square feet. So the program's pretty simple: a library, reading rooms, meeting rooms, admin, and back of house spaces for that. So not particularly difficult system to do. So here's kind of a look at the project rendering. Be twice the size of the existing original library that they're replacing, and they have a budget of about $33 million and currently under construction. But some of the interiors from the architect, you can see very modern but very open spaces, lots of places for people to read. So there's lots of natural light, and that kind of was one of the pieces they want to do there. So there's the team: architect, mechanical engineer, structural, lighting designer, and sustainability energy analysis. So the scope of work for that concept phase, we're going to do a climate analysis, shoebox modeling, and help set the goals for energy. Once move into schematic and design development, proposed and baseline energy models. So looking at how close we're getting to energy goals, looking at load reduction and efficiency measures, and then report and presentation showing there. And then finally is removing construction documents and contract administration, reviewing the drawings, making model revisions, and then at that point you're beginning to look at lead and code and local law compliance. So code compliance is there, so that's available for there. So this particular project was decided to go for LEED Silver, and for them, this is old enough that it was going against 90.1 2007, which was the local code for that at the time. So 25% savings, 30% energy cost reduction, so they could get additional city funding for that. So this is an example of where you might be on a spectrum, aspirational, so meeting the energy code and LEED silver, so you are doing better than the minimum code. LEED gold, you may be looking at 35% energy use savings compared to some baseline. LEED platinum, greater than 35% again, plus on-site renewables, really pushing the boundaries for that, plus a lot of other features for those of you who use LEED. And of course, most aspirational would be if we go all the way to the zero carbon standard and looking at how far we can get with that. I see Sean has asked, shoebox modeling. Yeah, it's a simple modeling. And Sean, I'll cover that a little bit more. We're going to talk about standard 209 in a bit, and we go through kind of different modeling concepts with that. But yes, that's the idea there. So just a sec. So moving on, some of the early modeling, energy modeling objectives, looking at the fenestration area, orientation, how that relates to the program requirements, how can you incorporate passive design? We talked about natural light being a key one there. In a lot of spaces, commercial spaces, probably not as useful to do passive in many aspects, but look for opportunities for comfort and being able to take advantage of natural light and solar processes throughout there. How to improve resiliency against climate change and natural disasters. That's increasingly important one as we're dealing with climate change pretty rapidly here. Being able to have the building operate, or at least maybe shelter people in case of a natural disaster. Opportunities for heating, cooling load reduction. How can we work on that? And which HVAC system type is going to work best for the type of situation and the operation we're going to do. And then finally, tracking design versus the goals is kind of the key thing there for the early design. One of the things they did, climate analysis. This is the climate tool. And so this is showing plots across the year, the hours. This is using standard 55, which is a comfort condition, and it's showing that the hours here kind of in the middle that are in the blue are going to be in the comfort, or some shading is going to give us almost 20% of that. And then there are other techniques for dealing with the temperatures that are colder, and then the temperatures and humidity which are higher as well. So the climate tool is actually a pretty useful tool to be able to look at that. You can bring in your weather file. This happens to be New York City Central Park weather file for that particular case. When you're looking at information about early design, the level of detail for the inputs is actually pretty low level. I mean, we're high level, sorry. We want to know about condition area. We want to know about geometry and thermal zoning, if that is specific to what's going on. In this case, this particular project probably did. How the envelope's going to perform, window to wall ratio, lighting, equipment power, design conditions for temperature and humidity, and HVAC description, and some sort of schedule. So we're trying to pull the pieces together, but we're not getting down into details so much in early design, trying to use what information we have. And you see some of the resources, the energy code, whether it's IECC or 90.1, and the user's manual for 90.1, as Sam mentioned, is actually a good resource for some of this data as well. And we talked about some of these other sources earlier. So one of the things that oh, sorry, I'm going to back up. Jose's asked if the psychrometric chart app, yeah, the climate tool is a free tool, and I believe we have a link to that later, or at least the URL for that. It's from UCLA, from the architecture department, and they continue to make updates for that. So on an early design project, one of the things we're trying to do is ensure quality, and one of the things you are looking at is what inputs, and trying to confirm with the relevant members of the team, is this what you meant in terms of building envelope? Is this what you meant in terms of systems and equipment? What are you designing to for that? So effective and efficient communication with a design team becomes critical. You've got to be talking about all the assumptions, and that's what they are at this point. They are assumptions about what's being done. So and one of the things you'll also be doing here is looking at some of these inputs that may flag a higher estimate. You know, if you're doing something that looks a little higher than traditional practice, then you may want to be looking at how sensitive the building is to that particular input. So Sam mentioned zoning simplification, and you see here the idea of trying to do exterior zones, perimeter zones, which are going to be affected by solar gains, by heat losses, heat gains because of the fenestration and the walls in the area. These tend to vary. Practice is somewhere between 10 and 20 feet. It kind of depends on what you're trying to do there. And you see different shapes and how they're trying to approach that in multiple cases, and so they would be, you would simulate them separately within your model. This is the idea of a geometry simulation simplification. If it's a single zone, for example, you don't need to put the individual windows in at this point. One of the critical things is windows are important if they're punch windows like that, if you're trying to look at daylighting penetration, and that's probably not something you're going to be doing a lot of detail on in early design. So that shows that the area windows can be just represented as a single window in there, or something that instead of individual shades, you could you could create a single shade that's more effective. This makes it easier to create your input, and also will help you meet the goals there. Other simplifications have an effective geometry that's the same for every floor instead of doing the variation. Anytime you introduce this sort of difference on floors, then you add complexity, because a lot of the tools make it easier to put a multiplier on a single floor, so you're not having to enter that. So in this case, the one on the right, I would have a ground floor which may or may not have exposure to a garage or to the ground, and then a top floor which has a roof. All the intermediate floors could be done as separate elements there. Another thing is to try to look at output, compare your output to the target and how you're doing, whether it's, in this case, the top left is energy use intensity, showing your design project, the target, and a typical other project, a median property. And that may come from something like Energy Star Portfolio Manager, which would be based on energy use of that typical building type. Also, you can look at the energy use by breakdown, the distribution there. You have an example. This is from DO2, and showing lights, task lights, miscellaneous equipment, space cooling, space heating, etc., all the way through the total. And you can see how that's split out by fuel. But also looking at the envelope performance. This is another output report from DO2 showing what the average U value is facing various directions, and that can help you look and make sure that you've not done something that's way out of line with what you expected. So your U values match up, etc. Other things is start looking at what is affecting the site energy use. What is your energy use? What's a loss? What's a gain? And you see two examples here. And this help show that window conduction is quite a large proportion of this. Not only the conduction, but the solar gains through that. So maybe we could look at reducing window area. Are there other ways of looking at it? Look at what the impacts from both sides are before we start looking at just the energy use. I should say back on this one, you could also look at higher performing envelope and other options to be able to do that, shading to deal with the solar gains as well. Envelope sensitivity, doing a study saying I'm going to change the R value of insulation and see what what difference it makes over a range of R values, so that could be a reasonable. So the yellow line shows an increase in energy penalty 40% as the window to wall ratio increases. So that's a direct relationship, almost 1-to-1. Shade heat, SHGC a little bit lower, but not quite the impact. Insulation levels for the roof and the walls, and you see recommended levels there, and overall U value, you can see how that affects that as well. So having a look at what it's sensitive to is very important as well. So space conditioning savings as well as other options. So as we move up, we're going to see more savings, percentage saving, but you see it does top out over a bit. So you're going to run to a point where additional savings are not worth the cost. Maximum sensitivities on that particular item. So, okay, I see a bunch of questions coming in. Luis asks how to communicate simplifications of the rest of the team, especially the decision making people. And I think you need to describe what you're doing as not is an early design action here. You're trying to look at what is important and find out what that is and work toward that. That some of the decisions that are made later won't have as big an impact as some of the ones you're looking at today. And so I think that's kind of the thing to be clear about it, is showing a graph such as the one up here right now, that glazing U value is really important. It's important to have good insulation values, but they are not contributing anywhere near the impact of the glazing. Also, the glazing percentage, and I think that's the kind of some of the keys there. Let's see. How big a variation do we see when we simplify geometry? 1% to 2%. It's not a lot at this point. There are many other things as you see the inputs around glazing percentage and U values are going to have a much greater impact than that geometry, except for shading, and I think that's really key. So even a large scale building is still going to be not insignificant, but not the driving factor at that point. Let's see. How would you decide to simplify the building in slide 157? Hang on. Back up. Get my cursor here. Think. Simplify, well, in this case, what they've done is just made all the floors equal in size, just to simplify simplify the geometry. I actually probably at this point wouldn't simplify it as much as has been done there, but from an area and glazing standpoint, those are equal. Let's see. What is the name of the tool I'm showing currently? I'm sorry, Jacob, which one or which slide were you talking about? Oh, the U-value analysis. Okay. That's actually not a tool so much as taking single values, starting with a baseline and then varying the U-value and plotting where it goes. So it's not, that's just a presentation of multiple simulations over time. So let me get through 160. Okay, and Jingwen, how do you simplify the shading as a total area, the individual shadings? Just the geometry. So in that case, what they did was just make sure that geometry matched the sum of the others. And essentially for that one, it was about a 45-degree angle if you looked at that particular case. So, okay. Here's a slide showing some output evaluation, trying to take a look at that. So we start with a baseline design based on 90.1. We go to our proposed design. In that case, we're looking at 29%. We look at some alternatives. A ground source heat pump, we can get even more savings. Fenestration area gives us another couple percent, just reducing it. At a 40 kW PV array really doesn't reduce the energy intensity, just at offsets. But if you look at it from a utility cost standpoint, the proposed design at 29, the ground source heat pump at 35 again, it's got some savings, but it's still quite high in terms of first cost. The fenestration is about the same, but then you see the PV array is actually able to cut the cost even more, partly because it's offsetting some of that electric load. So early design is when you can make an impact. You need to be able to walk through your analysis, showing where you got what you did, what you value, what works, what doesn't work, and I think that's really important. Recommend any further design improvements or things that you would like to work with the design team on getting there. Clear visualizations are really key, and I think that's a very good thing to understand. There is a project on the BIPSA USA website called Project Stasio, which is visualizations that many people have contributed for various aspects to try to tell a story simply, but in a visualization. Also showing preliminary life cycle cost, where you can look at incentives or funding options if you're trying to see, because many things early design, you're going to have an opportunity to reduce cost more significantly than later. And then what are the opportunities and challenges? What is it cost? Is it peak load? What are the options, and how would that be affected if you took that one out? So this is an example of level of effort. And this is a 2-week of staff time for that. And you see most of the time is spent in creating the assumptions and the initial modeling. It's not just one model, it's multiple models to try to be able to do with that. Take a look at the QA/QC, revise and rerun the models, look at the results, write the report, and then present, review, and wrap up, present the report. So here's kind of example of effective graphs to be able to show this. And again, the data presentation, the visualization to be able to quickly explain what you're doing is really important. Okay. So being able to show different types, what the EUIs are, what the source numbers, what the costs per year are, how we're dealing with graphs and the EUI ranges there. And you can see a residential 40 to 50 kBTUs per square foot versus 400 for dining, or maybe a collegiate building at 70 to 80. Here's different effective graphs. You can start with a baseline and look at the options for being able to get to lowest performance, and you show what those are graphically and show their impacts. so that you see college spaces that some of the options are not getting us very much gain for that, because probably high internal loads. So you can look at overall how those go together to give you opportunity to get to the lowest energy use. So summary, for early design projects, you're trying to look at what it is you're trying to evaluate, what you're trying to solve, and how building energy analysis, the modeling, can actually help answer that question. Selecting an analysis approach, including the appropriate tool. Sam mentioned earlier, no tool does everything, and some tools would be much better at focusing on HVAC equipment, some on daylighting, and it just depends on what you're trying to do. Don't try to force a tool to do something that it can't. It means that you're going to have you can't really trust the results there. So and your simulation tool could change throughout design, but input sources are important. Alternatives, what are the efficiency measures or carbon reduction measures, for example, that you're looking at? Have a QA QC process that you're comfortable using that allow you to make sure you're getting accurate results, so that you're documenting inputs and being able to look at outputs and being able to do that as well. Communication, pretty critical with the design team, so that you're communicating your findings, and so you're getting relevant information in a format that the audience will be able to digest. Jose asked if they are QA QC checklists, and I believe we do have some of those a bit later in the presentation. And finally, develop a plan for what you're going to do for your modeling. You know, what are the tasks, the level of effort, and the schedule, so that you know you've got X number of hours to be able to spend on a project or this portion of the project. And one of the things it says, everything you're doing here is based on a lot of assumptions, not just several. And so be ready to be able to change that as the design process moves forward. Again, I worked on a project very early, and the building shape changed from L shape to X with a big atrium in it, between schematic design, design development, and as we got into construction documents, we had to be able to be quickly able to change the model to being able to do that. Also, as you go through design, you're going to be able to get more information for that. So exercise here, what are the 3 largest energy use drivers, and what would you think you'd be wanting to look at for this particular case? So if you want to type answers to that in the questions, that'd be great. That's great. Everybody's coming in with the same sort of thing, that natural gas equipment is one of the big drivers, both space heating, domestic hot water, and then fans comes in as third. So that's a key thing. But I would also say that looking at the miscellaneous equipment is also something we should be doing as well. Great. Okay. Thanks, everyone. So we're going to move on here. So next, I want to talk about ASHRAE Standard 209. I want to move pretty quickly. We got a lot of slides, and I know it's already 2:51. So ASHRAE standard 209 is a standard for basically a process for doing energy simulation aided design. And so the only thing that is really important here is if you complete 4 activities and your project complies. It's pretty simple. You do a climate site analysis, benchmarking, energy charrette, and establishing the energy goals. There are alternatives, and you have to do at least 2 modeling cycles, what we call here. Simple box, load reduction, that one is required. Design refinement, design integration optimization, or conceptual design, HVAC system selection, or value engineering aspect. So you have to do all the above, plus a load reduction and one of the other ones, and then you comply for that. So climate and site analysis is pretty straightforward. This is another view from the climate tool, climate consultant, and so lets you take a look at some of that benchmarking. You can get for the US public data, looking at the median energy use intensity for a particular building type, this case offices in the Pacific Northwest or the Pacific Census Division. A charrette, trying to go through what are the opportunities and the option, getting the mindset of the team focused on where you are trying to get with the particular cases here. And then last, establishing the goals. What are we trying to do? Are we trying to go to carbon neutral, which the 2030 challenge does, or are we trying to set a specific target for LEED or other opportunities? And that's kind of a key thing here as well. General modeling cycle requirements, the energy baselines, input data, reporting, and quality assurance. So both QA of the input, but also the output, and doing the analysis for that. I'm sorry, I am moving pretty quickly here, but so simple box modeling might be done. You would do that early design, conceptual as well, and schematic, load reduction modeling and schematic as well. And HVAC system selection can be started in schematic, but generally tends to bleed into design development, design refinement, getting more details as the architect, engineers beginning to select particular items or specifications for that. So you begin to look at looking at it from an opportunity standpoint, design integration and optimization. And then finally, as we're moving late in design development, how can we use simulation to help make decisions on value engineering? Is this option really worth the extra investment, or is there an alternative that might get us to near the same thing but still meet the goal? In reality, very few projects do all of these. I've been on maybe 3 projects that were able to do everything from simple box modeling, actually pre-design from schematic, and we ran hundreds of simulations over the period of a couple years for a large office building. So you need, in 209, of course, you're going to choose 2 of those. This is an example for the simple box modeling. You're just trying to look at the energy end uses and demand characteristics for that. And you're trying to create models that have effective geometry and window to wall ratio orientation that can be done for there. So there's an informative Appendix C in Standard 209 that will help as well. So for that, we're trying to look at, you may be looking at aspect ratio, massing, orientation, number of stories, but we're also looking at fenestration, distribution, area, shading, skylights, opportunities, and what their impacts are. And this is all trying to learn what, for that particular program and for that location, what are the impacts. Insulation, we might look at comparing multiple roof insulation R values and seeing the value. You see in this case, beyond about R30 for that roof, it's not going to make a lot of difference. It's some, but is it worth paying to, effectively 50%, 100% increase in the insulation value? So daylighting, looking at different shapes to be able to look at that as well. Looking at lighting electricity, the square has the highest because its daylighting doesn't penetrate as far. Rectangle, a little bit better, but skinny, being able to fully daylight the whole thing can have the biggest impact. And if that's one of the options you're trying to do. Now, many sites are going to be constrained, so you may not be able to make the simple box or even simulate something like this for a lot of them. The other thing is to look at natural ventilation savings potentials. And I know in a lot of cities, this is not reasonable to do natural ventilation, but for many places, including where I live in Washington, D.C., natural ventilation is actually an effective tool for many parts of the year, except of course when there's pollution happening. So this might be an example you're seeing for this. Natural ventilation can offset any mechanical cooling needed for much of the year, except during the hottest summer months as well. So you can also look at base case and maybe an operable window with an interlock, and you see about a 10% savings there for that. The other thing is looking at resilience. What might be the temperature response if we lose our heating and cooling system? What might be the indoor and outdoor temperature? So there's outdoor temperature, and then what happens to the space temperature in that particular case? Is the building resilient to that loss of heating or cooling? So we have our loss of cooling, and because we have a low mass space, it's going to climb pretty quickly to match the outdoor temperature. If we have a higher mass space, it can offset that and push that to later times during the day. If we're looking also maybe in more detail, net zero energy or carbon emissions, we can look at electricity and natural gas consumption and be able to look at the emissions factors that Sam was talking about earlier. And also look at the opportunity for area for PV. Is that possible? This is a relatively recent project. It's actually a zero energy building at National Renewable Energy Lab near Denver. And in that case, you see the PV virtually covers. It's about 90% coverage on that. It's difficult to get more than that, but with the PV, you're able to get doing simulations, what the production estimate would be to offset what those CO2 factors may be. HVAC system, very simplistic, overhead, underfloor air, radiant and dedicated outside air, and displacement might be options that we're looking at for that particular case. For construction and occupancy modeling cycles, we have as designed, we have change orders, we have as built, energy performance, and post occupancy. And yes, I have seen as change orders in construction documents on a project where, for example, they wanted to compare different chillers, and chiller manufacturers had to provide curves for their specific cases in there. And this, you get kind of maybe a post occupancy look at that in comparing your actual versus the model and what's happening. So these are all optional within 209, but we want to make sure people understand that they're available. So what are the requirements for who does what in this? So the energy modeler is going to be doing the climate and site analysis, finding benchmarks for that building type and location. Charrette is where you get the designers and owners together so they understand the impacts for that. The goals come from the owners, and these are all part of the general requirements for that. Then the first modeling cycle, what are you trying to do? What is its purpose? The inputs, the baseline, and the goals. The analysis, input reporting, output reporting, and having QA not only by the energy modeler, but by all the members of the team that are affected for that to make sure they understand what the inputs and the outputs mean. And then finally, a second modeling cycle, we're just redoing that again. So ASHRAE standard 209 also is referenced in AIA's Architect's Guide to Building Performance. And they talk about the same sets of modeling cycles there. So they just put it in just a different format to be able to look at that. So it is getting referenced by a number of important documents out there. So question here, and if you want to put this in here, do you have a favorite modeling cycle? Is there something you like to do from that? And I want to clean up the queue questions thing. So is there something that you find that is particularly useful from one of these modeling cycles? HVAC system selection. There we go. Thanks, Kara. Anybody else? Design refinement. Sean says as built. And Margaret says as built as well. As built, change orders, conceptual. Okay, so wide range of things that we're looking for. Great. Post occupancy. Right. Design, integration, and optimization, a few people. Isaac also on as-builts. Okay, thank you. Great, thank you very much. So let's move on. So how might you think you use standard 209 in your work? Is there something that might help you in what you're doing for work today, or is that does it fit what you're doing already? So if you have an idea there, please go ahead and put that in the box, the queues. Yeah, cost analysis, different HVAC systems, clean energy master plan, great. Understanding the outputs better, prototype building comparison, using a guide for the modeling process, yeah, that's great. Structure to the modeling. Let's see, great. And Keith says would be great if all projects use so their permit applications are high quality. Great idea. Okay, anybody else? Okay. I've got two sections here. I don't know, we're running pretty close to, we're right at 4 o'clock. So actually we may push weather data to tomorrow, but I want to go ahead and go through this section on accuracy and uncertainty because they're kind of two different sides of the same thing. So how accurate are we looking? Is it 5%, 10%, 20%? What's the variation? Short answer, it's as good as your inputs. You can get quite accurate if you really have good data on that side. But it's also great for comparing relative performance, and that's where simulation shines. I want to compare two different windows, two different HVAC systems. That accuracy is actually quite high. It's okay for absolute energy estimates as long as you've got inputs that are good quality. If you've got lots of assumptions, you're not going to get there today. So you may have a calibration issue. The actual is coming in quite different from the model, but if you go back in and are able to look at what the inputs are and recalibrate that, you may be able to get, it shows here, a very small error for that. And calibration is important, particularly if you have an existing building. Some of the sources of uncertainty in the building model, you really don't know occupant behavior. We're making a lot of assumptions about that. An example might be you have two identically designed buildings, but they might be operated quite differently. One might have a 24-hour call center in it, the other may be lawyers. very different internal loads schedules. We generally know pretty well the geometry, the materials, and equipment efficiencies from that. But from the simulation, the load calculation algorithms are pretty good, but again, they're dependent on those inputs and the equipment models. And one of the things that is really important here is that simulation software that you're using has been really well tested. And that is kind of one of the keys for that. So how do we go about testing? One of them, compare to real data from a building or test cell. That's empirical. It's also very hard to do, to be able to get a very accurate model in your simulation tool that matches what is real data. Analytical verification, compare to something we know we can solve analytically. One of the biggest strengths has been comparative, though, which is comparing tools. And there's an ASHRAE standard 140 for that as well. So this method of test for evaluating software. So what this test does is allow you to compare two different tools for a number of different cases. And you see here, there are a number of tools over time. Transys is in there, DO2, and Energy Plus is in there. So there are a number of different tools in here, and there's some European ones that we haven't mentioned. But what we're trying to do is look at what is the solution for that particular one. And so this comparative test is actually makes it clear that if you're out of range for one change, and these are very simple changes in the inputs, to be able to isolate it. Every tool that works with standard 140 in this way and doing the comparative has found bugs. And I mean, that's tools that have been out there 30 years have been fixing bugs that they wouldn't have found another way. So this is an example of one of them. It's a thermal fabric test case. It's a pretty simple box that's 8 by 6 meters and 2.7 meters high with 2 windows in there. And you see the annual cooling loads across the various cases there, and you see some are quite close, others are not, and the variation for that. There isn't a pass-fail to this per se. There's been some work to try to look at what ranges of pass-fail make sense for this particular case. Or here's a comparative looking at monthly heating loads, and you can see all 6 tools are actually quite close in what they're doing. And so monthly is important to be able to make sure that you're looking at that, or even looking at a particular load, high load day, whether it's a summer day in July or a winter day in February, and see how they compare. And you see some variation off that for the day, which you would expect. So the other thing in practice, the input certainty just really dominates what we're doing here. It's clear that we have to try to provide as much information, but we can't predict occupant behavior. We can't predict weather. We can use past predictions and or measure data as well. So one of the things to deal with input uncertainty strategies, make sure you're prioritizing important input. If from your load analysis, windows and envelope is really important from the load aspect, then you really want to focus on making sure you've got accurate information there. Reviewing what you're using as input with a design team, making sure you understand where they're trying to go and identify a range of input parameters. And then from that, you can look at there's a lot of uncertainty around this, but it's only a 2 to 3% change. But around this one, there's a lot of uncertainty, and it affects the energy by 20% or more. So you do that through sensitivity analysis. You can also do Monte Carlo, and you want to show the ranges of results. It's important to understand what's uncertain and make that clear from what you're doing. And I'll catch up on question just in a second. I saw a couple pop in, but I'll do it. So how accurate is it? You may not know initially. And I think this quote by George Box, it really puts it very clearly for modeling and specifically energy modeling. All models are wrong, but some are useful. And I think the key is trying to make the models as useful as possible. So the exercise here, how would you rank these? And I'm going to try to clean up the questions. So think about this and okay. Jose asks, are simulation software required to meet this standard? That is actually a requirement in 90.1 these days. I don't know whether it will make it into into IECC or any of the state implementations for that, but it is now making it into the code that is important for that. Okay. Richard wants to know how Apache compares to these results. I don't know precisely. I'm pretty sure that Apache matches a lot of these. I've not seen results with Apache in results comparing to the other one. So, and then last, Jose, is BIM modeling capable to use in industry to account for all inputs and outputs that are described so far. So BIM is more of a tool for doing the three-dimensional description of that. And one of the problems I personally have with building information modeling is many of the BIM models I see don't have a lot of detail. They may not have the thermophysical properties you have there. And so that can be a challenge for that. As Sam mentioned, there are tools to convert from BIM modeling into building energy modeling. Most of those are best used within the BIM modeling tool, but I've seen other people also use GBXML, which was mentioned earlier, to create very robust models, but they do a lot of work on the building information model before they do the conversion. So let's see. Richard says 1, 4, 5, 2, 3. Sean says 1 is most uncertain. Sorry, I'm trying. Oh, okay. Jose's correcting me, saying not building information model, but BIN. Well, a BIN model is a simplified energy simulation model. It doesn't do an hourly calculation so much as binning of data, particularly climate data, for being able to do calculations. It doesn't deal with the interactions as well as some of these others. Okay, let's see. Sean also asked how to deal with complex systems that go beyond the limits of the modeling software. Jump to Excel is possibility, Sean. Also using other tools and depending on that. So some tools will actually use a lighting program called Radiance, which does very comprehensive. It's photogramically correct in terms of the you could create a picture from the simulations that come out of that. That's an example, and you'll see those where a program knows it doesn't have a particular good input or it doesn't do that well, it will often link to another tool. Let's see. High to low, Kara says 4, 3, 1, 2, 5. Jose says operating HVAC set points plug load, VAV error, and actual year is typical. And number of people said heating, cooling set points is number one. Luis, Robert, and others. And I think, like some of the others, this is a bit, there's no one right answer. It depends on a lot of different things going on in the building and where you are. So, and I want to stop because we're over 3 o'clock. Tomorrow we will pick up with weather data and deal with some of the uncertainty related to that. We have a number of unasked questions. I want to cover those tomorrow. Jose's asked covering modeling existing buildings and resources for that. And that's one key there. And then Sean's asking, how do we deal with older buildings? What's typical for that? Luke wants to know, is there good training specifically for eQuest? And I think you'd have to ask the eQuest people. ASHRAE doesn't offer simulation for specific software. But I think if you did a little bit of web searching, you could do that. So Sam, want to add anything?
No, I mean, you kind of ran through the questions. I guess we can also follow up with questions at the end of tomorrow. I don't want to hold people too long. I know we're already about a little bit of time over, so.
Yeah, I've captured,
we'll talk.
The questions so we can make sure we cover them tomorrow.
Yeah, but we'll definitely talk about existing buildings and where the data comes from those and calibration. There's a lot of examples for that tomorrow. So.
Great.
All right. Well, thanks everyone. We will see you back tomorrow at noon Eastern time.
Thank you very much.